current slide. All right, just a couple of announcements here. Okay, let's follow up with what we talked about last time. And one of these is student course evaluations are open for first mini-term courses, which is us. Have all of you started or done these okay already? Or you still got them yet to go? Okay. Please do these. These are very valuable to us, to me personally, and to us as a college, because we've got a SACS visit coming up within a year, and they're going to be looking to see what kind of percentages we have of students making their student course evaluations. So please, folks, get these done sooner rather than later. Okay? So there's that. I've told you before about Alabama A&M having this grant from the National Science Foundation for the North scholarships. Very, very nice deal here. They will pay your last 2 years of tuition if you agree to get into a field of math or science education. There may be some restrictions on it, but check it out. That's a really good deal. Okay. And the other thing is something that just happened today, and I can't tell you all of it because I haven't had a chance to follow up on it all. But I had to miss my 8:30 class last Tuesday because I had a doctor's appointment. I don't know if y'all remember. I have been back from it for a while, but I had that appointment, and the appointment was at 8:40, so I couldn't be here for my 8:30 class, and it lasted too long, so I even missed part of my 10 o'clock class, but we got that one met. So I checked with the class this morning to see when they wanted to make it up, and they said tomorrow morning at 8:30. So tomorrow morning at 8:30, I will not be on the Birmingham campus like I normally would be. I'm usually there from 8 to 12. Tomorrow I'll be here from 8 till 8:30 down in my office, then up here in this classroom from 8:30 to 9:45. Now, after that, I don't know where I'll be. I've got to check with my boss and see if there's anything going on that I need to be over there after 9:45, or if I can just work here for the rest of the day. I've got to go over there at some point because I've got to start the paperwork for the field trip on Tuesday. So I've got to get that taken care of. So whether I do it earlier or later, it doesn't matter. So I've got to find out which way I have to do that. So I can't tell you. I'll tell you exactly where I'll be, or planning to be tomorrow morning, 8 to 8:30 here, 8:30 to 9:45 teaching a class here, and then after 9:45 I'll either be down in my office or heading back to the Birmingham campus. I just don't know which right now. But at some point, I have to go to the Birmingham campus to get the paper right. Okay. Any questions? Please do the student course evaluations. Now, as far as I know, we have the field trip on for Tuesday, and we'll be leaving here at 1:15. Okay? Now, that means and y'all said you didn't need rides. Everybody was happy transporting themselves to Sanford. We'll talk about, in fact, I guess I ought to do that now. Does everybody know how to get to Sanford University? You don't? Okay. Are any of you who don't know planning to ride with me? So you don't need to know. Okay. You're welcome to ride with me. Okay. Here's how I get to Sanford from here. If you know a better way, take it, okay? But if you leave here going down the Western Superhighway, somehow get on 150. You know where 150 is? Okay. Get on 150 going toward Hoover, right? But you'll see, well before you get halfway to Hoover, there is where Lakeshore comes in and butts into 150. Take a left there. There's a light there, and it's a pretty major intersection. You can see that. Out in the middle of nowhere, but it's a pretty major intersection. Take a left on Lakeshore. Take Lakeshore all the way across. You'll go past John Carroll High School. You'll go past the Walmart and the shopping center they call Wildwood, and then Walmart and Sam's is in that. And go across I-65. Okay, once you cross I-65, start going down the hill. There's a light at the bottom there that's Green Springs Avenue. Yeah, I think it's Green Springs Highway, whatever it's called there. Okay? Maybe called Columbiana Road. I don't know. It's the same road, but it changes names. Go through that intersection. And there's a light there. Big light always stops you, it seems like. Now, you continue on Lakeshore. You will come up on at least one entrance that says Samford University. Don't take the first entrance, okay? Keep going until you get to the main entrance of Samford. That's got an actual light there. The first entrance is just a turn. The main entrance to Samford has a light. And don't go in the first drive because it's a U-shaped drive, sort of. The first drive is coming out. The second drive is going in. So you go into Samford, and you go up the hill, and the first cross street that you come to is called Montague. Take a right on Montague. Now, Montague goes like this, and it makes a gradual left, and just after it's made the left, there will be a stop sign for a pedestrian crosswalk. Then you'll get another stop sign for a pedestrian stop walk. That's where the planetarium is, that second. And it's real close to the first one. Okay? Now, what you do, just past the planetarium there, that stop sign, look down in this parking lot. If you see a vacancy down there, you can take it. Okay? At that time of day, I would expect not to find a vacancy. Not to find those spare parking place. So what you do is go on up the hill, and right at the top of the hill, when you start making a bend around, you'll see another parking lot. It's very well disguised, okay? There's a little parking lot out here, and then a parking deck, but it's covered with vegetation and stuff. You hardly will notice it. In fact, our Mr. Hank Wade, I think, designed that to blend in with the campus so it wouldn't be an obvious parking deck. But it is there, okay? So you can turn in there and look for parking places there. Most of the time, I found them there. If you can't there, go to the very next one, and it's the upper part of the parking deck, and I think you can probably find one there. So if you can't find one here, there, or there, okay, I don't know what to tell you to do, but usually it's a busy time of day, but maybe spring term isn't as busy as last fall was. Last fall, I had to drive through the parking deck to find a parking place, and I did find one before I went up on top. Okay, so that's how you get there. Any questions on that? Did that make sense? Do people know the area? Okay. Now, if you want to follow me there, be here at 1:15, because we're going to leave here at 1:15, and you can follow me, and you don't have to know the directions, okay? But if you're driving from somewhere else and just going to go straight to the planetarium, then do that. Get to Samford. When you enter Samford at the main entrance, and you can tell it's made of big gates there, nice looking entrance there, two-way entrance, one going in, one going out, big gates and things. And you're going up a hill, there's a big building, it's I think the library at the top of the hill. You don't get that far, but it's big entrance, very nice looking campus. The very first cross streets, Montague, take a right, and then as you bend around the second pedestrian crosswalk, that is the planetarium, then start looking for parking. There's a little lot here, a bigger lot up on top of the hill. Hopefully you can get one in those two places. Okay. Now, the more you can carpool together, the better. Because like I said, there's not a lot of parking there. There's a fair amount of parking, but there's a lot of cars there that's already taking up the parking. So the more you can carpool together, the better. And like I said, I can take up to 2 other students comfortably. 3, a little crowded in the back seat, but it's an SUV, so you've got room. And it's not that far. So we'll meet here at 1:15 and go from here. Okay? Now, as long as no one needs, not that many need a ride, no more than 3 or 4 people need a ride, 2 or 3 people need a ride, I won't have to get a vehicle. But I'll be glad to get the vehicle if more than that number want a ride. I hear not, just one. Okay. Well, I can take 2 more. Okay. So we'll be leaving here at 1:15 on Tuesday. Now, I'm going to be trying to arrange to the field trip on Thursday then for chapter 23, weather and climate. If we can't get it Thursday, we'll try it again Tuesday. But if I'm not mistaken, that's the last day of class, isn't it? So we could do it final exam day if you wanted to. Have the weather, the Channel 13 on that day. Y'all want to do that one or not?
I'd like to do it.
Okay, so let's try to make that one. Okay. But like I say, I've got to get in touch with Jerry Tracy, and I don't know, he's hard to get in touch with. So I'll call the station and talk with somebody and try to get him to respond. Okay. Is there a question? Okay, I'll be glad to try to answer it. What about the paper? The words aren't important. Okay, it needs to be double spaced, regular type, 12 pitch font, double spaced, and it has to be at least 1 full page of text. Shoot to have between 1 and 2 pages. Huh? 1 to 2 pages. It doesn't need to be all that long. Okay? Now, if you go longer, some people do, that's fine too. But if you go shorter, you lose points. Okay. But shoot for 1 to 2 pages. All right. Any other questions? All right. That leads to another point. Please get the papers in. So far, I've received 3 out of, 15 students left or something like this, 16. That's not a good batting average, especially this late in the term. And then every lab and every test, I'm missing 4, 5, or more students from turning things in. So please get those in as soon as you can. All right, any questions? I had one guy come in and make up several today. Okay. So, where we left off last time, if there's no questions, we're in chapter 23, which is weather and climate. We're still in the weather part, and we're on major storms. Okay? Now, what makes a major storm is a rapid, violent weather change. Okay? Not just going from a 40-degree day yesterday to a 60-degree day today. That's not rapid and it's not violent. Okay? But if that temperature change also brought with it thunderstorms and that kind of stuff, yeah, that would be major storms. These are often associated with a frontal passage. We talked about that yesterday, where a cold air mass is pushing into nice, warm, moist air. That's going to create problems. Or when a warm air mass is pushing over a cold air mass, usually those don't create as major of a storm as the other. So here are the 3 types of major storms. Thunderstorms. We had some last night. We had some yesterday afternoon. This is February. We don't usually have thunderstorms then. I don't think these were major or violent, but they were making a lot of noise. Tornadoes, hopefully we won't have any, but we have had plenty. And then hurricanes, we're in the part of the country that does have effects of those hit too. So we'll talk about those in order. So let's start with the thunderstorms. Usually, not always, but usually develop in warm, very moist, unstable air. There's that unstable air again. Okay? Now, most of the time that's caused by the cold front coming in. Remember, these are usually caused by fronts. Cold front coming in over nice, warm, moist air. Think Gulf of Mexico air. Okay? and that cold front comes in, forces the warm air up. There's your unstable situation. As it rises, it cools, and it starts the thunderstorm. So let's look at the three stages of that thunderstorm. Okay? The first is called the cumulus stage. Now, had we gone over the previous chapter, chapter 22, which was the atmosphere, we would have already had the clouds. And one type of cloud is the cumulus cloud. These are the ones that usually have the big thunderstorms. Okay? And this is the cumulus stage. This is when you form those cumulus clouds. Associated with convection. Now remember convection, the warm, moist air going up. That's one cause. The mountain barriers, that could be another cause. Or the cold front, and that's the one I just described. Cold front coming in. So this is going to form the cumulus clouds. And what it is, it's uptake. That warm, moist air is, because it's less dense, it's forced upward. Now remember, because we're on a spinning globe, if you have movement upward, it's going to get a little bit of twist to it. Okay? And that is we'll talk about a little bit more later. Now, so right now the cumulus stage is forming these huge, huge cumulus clouds. Now notice these go up to an altitude, right now this looks about 9 kilometers, which would be 5.4 miles approximately. Okay? This next stage goes up to maybe 12 kilometers, which would be about 7.2 miles high. Those are getting up there. The next one may be about the same. Okay? So, first you have the uptake, the building of the cumulus clouds, warm, moist air moving up, getting into an unstable situation. Here is where the cumulus cloud gets mature. The updraft can no longer support, okay, because remember, warm, moist air. We're miles and miles into the sky. You're getting some cold temperatures up there. So that warm, moist air, now the moisture in it is beginning to condense. And not only is it condensing, it's getting so cold up there, you got ice crystals growing. But the updraft just keeps pushing them up and pushing them up because of convection. Okay? But at some point, they get so weighty that they start coming back down. Okay? Now, those are ice crystals, snowflakes coming down. This could be in the middle of summertime. It certainly can be now in February. Okay? But as it falls, the frozen water melts and becomes rain. Okay? Now, if this is what they call one of the supercell cumulus clouds, then what you have is more updraft coming up here, so the ice crystals keep just going up and down. They start falling, then they get caught by another draft of air and carried back up and down and up. And what's happening, every time they're growing bigger and bigger. Okay? More ice every time they go through this. And that is what forms hail. Because those ice crystals that would have just fallen as rain, melted and fallen as rain, they keep getting transported back up, building bigger and bigger, and then it can't hold them anymore, and they come down as hail. And hail can do a fair amount of damage. I don't know if you've ever had roofs that were damaged by hail. You may have had cars whose paint has been damaged, actually dented by hail. I think I've even heard of windshields being cracked by hail, big enough and strong enough wind behind it. But what I really dread in the springtime is if that hail is falling on the peach trees. Because if those peach trees have bloomed and they got those nice little peaches that are growing and the hail hits, there goes the peach crop. And I love my peaches in the summertime, so I don't want that to happen. And it happens to other crops as well. I just pick on peaches like that. Okay, so that can form hail. That's something we don't want to happen. And then finally, your final stage, all the updrafts are exhausted, no more there, and everything is just falling out. Now this sounds and feels like we've had happening repeatedly over the last several days, and probably still have a day or two more of it. I swear I can't believe how much rain we're having this week, but they were predicting it, and they said some places could have up to 6 inches this week. I think we're getting pretty close to it in a wide swath of areas here, because last night, I mean, usually I sleep through anything. Last night, the lightning and thunder was so strong, it woke me up. So, that's saying something. All right, now let's talk about lightning and thunder. All these updrafts and downdrafts, you got, and circulating precipitation. What happens with that is you get air molecules rubbing into other air molecules, and when you have that kind of friction, sometimes you knock off charges. Now, all materials have electrons, okay? The protons and the neutrons, they're stuck in a nucleus. You don't want them separating. If you have, you got a nuclear reaction. You don't want that happening, okay? But the electrons are in a cloud outside of that, and it's relatively easy for those electrons to get bucked around, knocked from one object to another. And when that happens and you separate the electrical charges, one part of the cloud could become positively charged where they've lost the electrons, and another part of the cloud could become negatively charged where it's gained the electrons. Okay? Now this is in one big old cumulus cloud here. You can have several different charge sites here. Okay? Now, 3 types of lightning you can have. Okay, wait, sorry. Charges accumulate in different parts of the thunderhead. Okay? And trying to make out nice looking figures, but I don't know that. I know what they're trying to do here, but it's a little hard to distinguish. Okay. The charges accumulate in different parts of the thunderhead depending on where the movement is. And what lightning is, when this charge center here, very positively charged, is getting close to one that's highly negatively charged, and they get close enough and the charges keep building, positives and negatives, keep building, and they get closer together, at some point you're going to have a flash of lightning. Now actually, you can't tell which way this is going. This is going from negative to positive. Always goes from negative to positive. Always. Okay? Discharge between the centers. Now, the charge can be cloud to ground. That would be this one. You get a negative charge center here on the cloud. That cloud is close enough to the ground. And what happens, the ground is big enough, it's fairly neutral, except when the negative charge gets near it, then it attracts the positive charges from the ground, and then you have a charge separation here, and then if that gets close enough and you get a big enough charge difference, you have cloud to ground lightning, going from the cloud to the ground. However, okay, if this is a positive charge center here, now here's the thing, don't read too much into this. They're showing rain over here as if it only rains in this part. It could be raining anywhere there, so don't think this has anything to do with the rain. They just drew it that way. They probably copied the one from before or something like that. You could have a positive charge site here. That's going to attract negative charges from the ground. And if that charge difference gets big enough and they get close enough, then you have literally ground to cloud lightning. Now you don't think of the lightning coming from the ground going to the cloud. It can. Now I have actually seen pictures that someone just happened to snap at just the right time when a thunderstorm was happening, and it caught want to say spark, but that's way too, a charge of lightning going up from the ground to a cloud. You can see the clouds up here, the ground's down here, and you see the cloud, the lightning starting from the ground moving up. It's amazing, but it can happen. It can kill you just as easily as this can. So there's no difference. You still get electrocuted. Or the third kind is cloud to cloud. Cloud to cloud within a big storm thing, or one cloud to another cloud. And that's always opposite charge centers. Now, just a little naval tale here. We were somewhere in the Pacific, out in the middle of the ocean. Nobody else around us. I was on an ammunition ship. Nobody likes to be that close to an ammunition ship. You know, they don't want anything happening. The only time they're close is when they're rearming. And this wasn't the case. We were just traveling. And I had what they call the dog watch. It was either the 6 to 8 or the 4 to 6 or 6 to 8. They split it up so you could eat supper. I was on one of those and went up to the bridge to stand the watch, and it was the most incredible display of cloud-to-cloud lightning I've ever seen in my life. The whole sky was like spider webs of lightning. It wasn't super big strikes. It wasn't super loud thunder. It was just sort of a gentle roar, and sometimes you didn't even hear it, but the lightning was just all over the sky. For 2 hours, it was all over the sky. And it wasn't even raining at the time. We just stood out there with no other ships around and just were marveling at the display of lightning. Cloud-to-cloud lightning. Okay. Now, can you have lightning with no thunder? Not really. You may have lightning, you don't hear the thunder, but it's going to thunder somewhere. Can you have thunder with no lightning? No. Okay? You may not see the lightning, but if you're hearing thunder, it lightens somewhere. And here's why. When lightning strikes, wherever it is, cloud to cloud, cloud to ground, ground to cloud, whenever it is, you have a huge discharge of electrical energy. And that electrical energy, number one, it's hot, and so it expands the air right around it, okay, and really quickly, and then as the lightning passes, it then collapses on itself. That creates an enormous pressure wave, so that is what you hear with thunder. It's a huge pressure wave. Now, the lightning that was happening last night, of course, it was dark and it showed up better. With the blinds closed, you could just still see bright flashes, bright flashes. And then within a few seconds or minutes, you would hear rumbling thunder. Okay? So anytime there's lightning, there's some thunder produced, whether you're close enough to hear it or not. If that was far enough away, you might not be able to hear it. Or, if it was dark enough, the clouds thick enough, it may have lightning somewhere on the other side of the clouds, you didn't see it, and then you heard the thunder later. So it could be either way, but you can't ever have lightning without thunder, or thunder without lightning. Okay? One causes the other. So it can't happen on its own. So that's a thunderstorm. Any questions on thunderstorms? The next is probably one of the most violent, the smallest and most violent weather disturbance we have. A thunderstorm can be big, broad, but it's usually not super bad unless the lightning hits you or the winds are strong enough that you have some damage happening. But a tornado, even the lowest classification of a tornado, can cause an enormous amount of damage. Okay? So what is it? Remember I said anytime you have the rising or falling of air in these supercells, you're going to get some twisting motion because of the Earth's rotation. So a rapidly whirling column of air, that's what a tornado is. And they mentioned the average diameter, 100 to 400 meters. Now, does anyone have a good concept of what 100 meters is? Okay. If you don't or do, if you're from the South, you probably have a fairly good concept of what a football field is like, right? Don't you? The length of a football field, including one end zone, is about 100 meters. So a tornado, the smallest tornadoes are going to be at least that wide, most of them, okay? Now, they may not always touch the ground, but they will be at least that wide. The 400 meters, on the other hand, would be 4 football fields placed end to end to end. That's pretty close to a quarter of a mile, okay? 400 meters is probably bigger than a quarter of a mile, okay? Closer to it, maybe a third of a mile. This is on the conservative side because some of the tornadoes that hit back in 2011, wasn't it, when we had the super bad, okay, was it April 2011? I think around Tuscaloosa, there was a city in, I think, northwest Alabama called Phil Campbell or something like that. There was another one that started with H. There's several places. The tracks that were left by those tornadoes were close to a mile wide. That is big, okay? And this is the smallest and most violent weather disturbance. They usually aren't that big. That's usually more like what you got, from 100 meters to a quarter mile, something like that. The wind speed can be up to 480 kilometers per hour, which would be, second, about 300 miles an hour. Whoa! 300 miles an hour wind. The damage produced by the high winds, that's part of it. Believe it or not, a drop in pressure at the center. To create that much energy, that pressure difference is huge. And people who have been near or in tornadoes before, they will tell you how eerie it feels, okay? And that's because the pressure just drops like crazy. Now, most of the time, this is the most of the time, the pressure drop is so bad, and if your house is in it, usually what happens is it sucks the windows out rather than blowing them in. Now, there is an exception coming. We'll talk about that. It actually, windows break outward, not inward, because the house is at a positive pressure. It suddenly drops on the outside, so they go that way. It literally lifts the roofs off the houses. It doesn't blow the roofs off the houses. It lifts them off because the pressure is such a drop right there in the center. Now, don't say, oh, we're safe inside the window, because it's going to blow out. No, you're not. Because if that picks up a limb from a tree and blows the limb into your house, no, you're not safe if you're anywhere near a window. So that's why in our weather situations, you go down in interior. Down in interior. You don't want to be in a room with windows. Okay? Flying debris can sometimes be some of the worst of this. Did anyone see the old movie Twister? Helen Hunt, I don't remember who the guy was in it. They actually had cows flying around. I think that was a little bit of a stretch, so I'm not saying it couldn't happen, but that's usually a little big for the debris. It's usually smaller than that. But cars have been lifted off the road and bumped into other cars. I mean, it can be pretty intense. These are usually associated with the intense thunderstorms, what they'll call the supercell thunderstorms. These are the ones that usually create the tornadoes. All right. Here's a picture of one. I'm pretty sure that one's bigger than 100 meters across. That is one big. I think this may be Dallas, Texas, or there was one similar to this in Atlanta I've seen pictures of. It's not the same one that's in your book now. It was on the earlier edition. This one in your book was Marquette, Kansas. I think that happened just a few months after the ones hit here in April of 2011. That was a really, really violent year. This one is much bigger down here. What is it that makes this color? What is it that makes it so you can see it? It's all the dirt, dust, and debris is picked up and swirling about. So inside that, you don't want to be. I mean, there's stuff in there going at very high rates of speed that could just utterly go through you. Now, a very small tornado hit our area of Georgia back when I was probably junior high or high school. And literally it lifted the roof off a house that we drove by on the bus going to school. I mean, it lifted it up and dropped it somewhere else. Literally lifted the roof off the house. That's the low pressure. And it wasn't a very big tornado either, so it wasn't nearly this high speed. Okay? That same tornado later I heard about, they found a pine needle that was sticking out of a power pole. And we went, wow, strong enough to force a pine needle into a power pole. You know, big creosote power pole. They said, no, it wasn't forced in. That was on its way out. It had gone all the way through the power pole and was on its way out before it hit enough friction to make it stop. That's an unbelievable amount of energy. Okay? It's pretty incredible. That house that had the roof taken off, just lifted off the house, most of the house was totally destroyed, but they said there was a table in the kitchen with a vase of flowers in it, and it just stood there. Everything else was destroyed, so it can do some weird things. Jerry Tracy has told the story, some of the times we've been there, of a woman who hadn't been paying it, she didn't have the news on, so she didn't even know. This was back before they had the warning systems, or she was not close enough to hear one, and a neighbor happened to give her a call, or she called the neighbor, and the neighbor said, "Aren't you getting ready for the tornado?" She said, "What tornado?" She said, "There's major weather storm coming. You know, you better get." And she couldn't go anywhere. There wasn't any time. So she went to crawl into her crawl space, and there was just a little opening. So she was literally crawling in when the tornado hit. She grabbed a foundational pillar that was under the house, held on for dear life. It ripped her shoes and one sock off. She never saw that again. Her feet were outside. It literally, the low pressure, there's both shoes she never saw again, and one sock. One sock, for some reason, stayed on. And she was holding on for dear life, or it would have sucked her right out, too. So there's not anything to play around with. Okay. Boy, that wasn't much on tornadoes, was it? And again, this map, I think they're going to show it in a while. Why they don't show it now, I'm not sure. The tracks that tornadoes make across the U.S., the customary tracks, we'll get that in a minute. Okay? I think. So let's move on to hurricanes. Or maybe we already passed it. I don't recall. Okay. Yeah, we probably already passed it. Okay? Now, before we get to the hurricanes, let's take a look at this. There's a hailstone I don't want falling anywhere near where I live, okay? Or anywhere near the beech orchard, okay? Or vegetable crops or anything else. Because that is an enormous hailstone. By what they're showing here, it looks to be about 4 inches in that dimension. That is huge. And if that's coming from a far distance up in the air, and that has quite a bit of mass, and the wind's blowing hard, that can do enormous damage. So, just wanted to point that out before we got there. So there was tornadoes. Now, what sort of irritates me is this thing on tornado damage they completely left off. Later, they're going to have the one on hurricane damage. What I'll do is I'll compare the two at the time. They're in your book on opposite pages. The tornado is on 586, the hurricane on 587. Okay? So, here's what a hurricane is, or how a hurricane works. Again, I think what I'll do is get blood for you. Now, remember, warm, moist air rises. Where do we get the warmest, most moist air? Over the oceans near the equator. And I'm going to point out one band right here. It's Eastern Africa, okay? And I don't know if you remember this or not, but near the equator, the winds are prevailing easterly, okay? The winds come from the east and blow this way. Actually, what's happening, the Earth is turning underneath the atmosphere, and it makes it seem like the winds are blowing from east to west. But that's what you get here. So, warm, moist air rising upward creates low pressure. And that's called a tropical depression, an area of low pressure. Now, that's always happening, okay? And in a tropical depression, the winds are generally moving about 55 kilometers per hour, which would be in the neighborhood of 45 miles an hour, maybe. Is that right? Something like that. Or less, okay? Tropical depression. Now, if that continues to build and you have more and more updraft, and the pressure drops lower, then you could move into a tropical storm. This is a more intense low pressure area, okay? They mean that several ways. The difference in pressure is much greater, much larger, lower pressure, but also the more intense area, okay? Now the winds are between 56 and 120 kilometers per hour. Let's just call that 60, up to 60, 65, 70, 72 maybe even miles per hour. That's getting up there pretty good. That's a tropical storm. What a hurricane is, if it continues to build and continues to build, and it happens, then these very intense low pressure areas are formed. The winds are in excess of 120 kilometers per hour, which would be in excess of 72 to 75 miles an hour. Now you have a fully developed hurricane. Now, we'll talk about the classes later, but a fully developed hurricane has a very calm eye. The eye of the storm, you've heard it called. Storming all around it, pretty calm in the interior. And you probably have seen that, and we'll see some illustrations of it, but the picture on page 586 is now they say it's an illustration. I would have thought this was actually a picture. It sure looks like a picture to me. Maybe they mean that, okay. Observing the hurricane's eye, a satellite observing the hurricane's eye, and the counterclockwise motion. So that means it's in the northern hemisphere. You can see that motion. The eye is that hole in the middle, and actually if you were in there, you'd feel it perfectly calm. It'd feel weird because the pressure is so low, but it would be perfectly calm. But you would look out around you and you see walls of enormously rapidly moving winds and rain and everything else, and you're perfectly calm. And you can see it within sight of where you are, okay? And if you were to go over there and try to penetrate, you would just get literally torn apart, almost, because that wind's so strong. That is called the wall of the eye. And it just goes from 0 to enormous speeds in a fairly short distance, okay? So that's the calm eye. surrounded by intense rain and thunderstorms. Really, really intense. Okay? Now, there's a picture taken from above of a hurricane a lot like this one, and you can see the counterclockwise spinning like this. There's the eye. If you're in there, perfectly calm. Right here around the eye wall, incredibly intense. Winds, rain, thunderstorm, everything, but in the middle, perfectly calm. Has to be one of the worst or most eerie feelings ever. I've never been there. I don't want to be. I actually had a friend one time. Can you believe that? Okay. When I was in grad school, he was an undergraduate at the University of Georgia. And he was a forestry major, but his dad was a pilot, I think, for Eastern Airlines, which doesn't exist anymore. And Doug had always thought he wanted to be outside, but then the closer he got to graduation and stuff, the more he thought, I really want to fly too. So he graduated from forestry school, and then went on to getting his license. I think he already had a private pilot's license because Dad was a pilot and he knew how to fly. He went on and got it. But it was back at a time when we were sort of in a recession and the airlines weren't hiring. In fact, the airlines were crumbling. That was about the time the Eastern collapsed and TWA collapsed and Pan American collapsed and Ozark collapsed. The airlines were crumbling and they were being bought out by bigger airlines. And so there were excess pilots out there and not very many airlines hiring, especially new guys. There were plenty of old guys with lots of experience who were looking for work. So Doug just hit it at a bad time. So guess where he went to work? For NOAA, National Oceanic and Aeronautic Administration, NOAA. And his job was to be a hurricane jumper. And when the hurricanes would come, he would go out, fly really, really high over them, and it still must have been really rough. He was in these great big old planes like passenger aircraft, but they were filled with scientific equipment and probably had a good contingency of weather meteorologists or others aboard. And he would fly over it and then descend into the eye and take his measurements, fly around in the eye. They would be taking their measurements, and when they got them all done, lift up out of the eye, try to get as high as they could so they wouldn't be shaken up too badly by the storm. I bet you it's still pretty shaky, and then fly on back home. And that was his job. He was a hurricane pilot. That's what he did, fly into the eyes of storms. Yo! Okay. Now here's what's happening. Picture that eye from the side. Now, you were up there looking down, and you saw the counterclockwise flow of air around. This is a cutaway view, because otherwise you'd have the wall here and the wall in the back, and you couldn't see anything. So this is a cutaway view of what that hurricane would look like. This is sort of a typical one, not a monstrous one, but not a tiny one either. Okay? This is the eye, and this is very, very, very low pressure in the middle. So what happens is, and it comes from the uplift around it, so you have air coming downstream like this, trying to equilibrate that low pressure. In moving downward, the spin of the Earth creates the counterclockwise rotation around like this, and then the air comes down and warms up as it comes down and picks up moisture and then goes back up. So you have all these motions going back up again, creates the spin. Okay? The eye is in here, and they show the eye here as being about, about maybe 15 to 18 kilometers from the center. So that would be a total of about 30 to 35 kilometers across. 30 kilometers would be about 21 miles. No, 18 miles. Okay? So let's say 20 miles would be the distance here in that eye. Okay? And then here, the walls, this is where the storms are raging. They're spinning like crazy there. And then the warm air is pulled on up and pulled on up, more and more air. The more you got, the more it fuels this thing. Okay? And the more it's going. The worst part of the storm would then be from about 10 kilometers out to probably 40, maybe a little further than that, and you have enormous damage there. Hurricane winds there between, it looks like about 18 and 55, say, on either side, all the way around. And the maximum winds are usually right in there near the wall, right in the inside portion of that, in the hurricane wind. Then you have what they call the gale winds out here. They're not quite as strong, but they're strong enough to still do a lot of damage. And the maximum winds and rains are near the eye, but outside the eye. So they're monsters. They are monsters. And they will travel, and that's why I brought out the globe. They start as your tropical depressions and sometimes develop into tropical storms and even hurricanes here. And because prevailing winds carry it this way, and then they start getting into temperate areas, and that's why they start bending and moving up the coast. Remember a few years ago, Sandy hit New York City and New Jersey really, really hard. Did enormous amounts of damage there. A few years before that, they made their way into the Gulf of Mexico, and you had Katrina and Rita in the same season. Enormous amounts of damage. Really, really powerful storms. So these islands out here usually just get walloped by other storms. Cuba, Jamaica, Bahamas somewhat, Dominican Republic, and Haiti there on the island of Hispaniola. Here's Puerto Rico here. Boy, Puerto Rico got really spot by Maria, wasn't it? A couple of years ago. They still haven't recovered. These can cause enormous cost of damage. Okay. No, they don't have these tables in here, so I'm going to go over them quickly. I thought they were going to show up here. Let's go back to tornadoes. They have a classification scheme. I think they call them EF blah, blah, blahs. I don't know what the EF, I've heard it before, but I can't remember what that stands for. Something forecasting, I don't know. And they have 6 classifications, the lightest one being an EF0, okay? EF0 storm. We had one of these go through the farm in Georgia. And they say they're not very powerful, and they're not compared, but I swear it cut a swath of really densely wooded area in my mother's yard. She's dead now, it's my sister's yard now, but a swath there that was good 20 yards wide. I mean, just took out every one of those big old trees that was in there. Maybe didn't uproot them, but it damaged them enough, took the tops off of them, damaged them big time. It made its way up, this was so bizarre, went up and hit a big magnolia and that was fairly close to her house, and twisted around. I don't know how it did this, twisted around her house and took out my dad's shop. Now, he was already dead by then, but he had built the shop back there just out of concrete blocks, nothing super sturdy. There was hardly a block left on top of another block. I mean, the roof, I don't think they ever found. And the blocks, they found only some of them. It hauled them off down into the woods somewhere. And this was an EF0 storm, okay? And it caused that kind of damage. To her house, it did a little bit of shingles on the roof, and one corner of the porch, it moved the post a little bit. Went wrapped around the house and didn't hit the house directly anyway. Okay, that was EF0. That's winds under 120 kilometers an hour, which is about 75 miles an hour. Now, if you go over and look at the hurricane side, that would be your Category 1 storm. That would be a hurricane. That's a EF0 tornado. Okay? EF1 tornado would be from 76 to 112 miles per hour. That's almost a Category 2 hurricane. Okay? Of course, you know, remember, now the tornado is much, 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 much smaller, so it won't cover nearly the area, but can be more intense right where it hits. An EF2 tornado, that goes from 113 to 155 miles per hour. That covers a 3 and a 4 hurricane. Hurricane Category 3 or 4. Okay? Then an EF3, which is just about the middle, severe damage. Winds are 156 to 205 miles per hour. That is your strongest catastrophic hurricane, Category 5. Okay? You're actually more wind in the tornado, EF3. You still got EF4 and 5 to go. So this is incredible how strong and how powerful those tornadoes are. EF4 goes from 206 to 260 miles an hour, and then finally the EF5, which we had that day in April of 2011. I can remember seeing the weather map and hearing them say, well, we're only tracking storms of thus and so strength or greater, and only those within the few miles of our thing. We can't cover them all because there were really powerful storms. EF5 storms, I think I remember seeing at least 3 or 4 at once hitting different parts of the state of Alabama. It was just an unbelievable weather day. Okay? So EF5, incredible damage, winds from 261 to 318 miles per hour. That's incredible. All right. Let's move on to 587, which is weather forecasting. 23.3. Some of the things they say here, I don't know if Jerry Tracy would agree with or not. He might. But weather forecasting is based on mathematical models of the atmosphere. Right there is a problem. Okay? Our atmosphere, I think like we mentioned before, goes miles and miles and miles up into the sky. I mean, lots of miles up into the sky. Okay? It covers every square inch of the Earth's surface. Okay? That high above the Earth's surface. Okay? That's a lot of atmosphere. So they're trying to do mathematical models of the atmosphere. And guess what they got for input? Okay? They send up balloons to collect data, weather balloons, I think twice or 3 times a week. And they only sample that area where you're going up. Okay? Not a very big area. Okay? They also have aircraft flying around that are collecting data and sending them back. And things like this. So with that very limited data, they have to make a model of this huge atmosphere covering the entire Earth. Okay? They can't do it, number one, so they just focus on smaller parts. But that's what it is, a mathematical model of the atmosphere. Now, my wife likes to listen to the ABC station, which has James Spann on it. And it seems like always he's saying, well, this model is saying this, but this model is saying that. So there's bunches of models out there. And none of them are any better or worse than the others. Some of them are more accurate sometimes, others are more accurate other times. So if they were inaccurate all the time, they wouldn't even use them. So there's bunches of different models out there. Now, in order to get those, they take that limited amount of data and they're making literally billions of calculations of what that weather data is showing them, and they can't do that without supercomputers. Now, I'm guessing the one they use is the Cray supercomputer up in Huntsville. That's the one I know that this college uses. So maybe they have their own. I don't know. But they're doing that. It's the only way they can build the models. Now, here's what they claim. These are fairly accurate forecasts up to 3 days. But every time I see a weather forecast, they give you the 7-day outlook, right? Up to 3 days, fairly accurate most of the time. Anything beyond that is mere speculation. The good news is, not too many people track and see, well, what did they say was going to happen 7 days from now? And then tomorrow, well, is that changed any 6 days from now? Well, the next day, is it changed any 5 days from now? If you did that kind of collection of data, and just move back a day every day, you'd see that that last day just was all over the place. Of course, not talking always the last day, but, and only when it gets within 3 days is it fairly accurate. What's the major uncertainty? Insufficient technology to connect the small and large-scale events. Jerry Tracy also, I can remember him saying a few times, that there are several markers they use when they're trying to determine if it's going to be a bad weather day, okay, as in tornadoes. Some of these involve way, way, way up in the atmosphere. Sometimes it will involve things closer to the earth. It'll be just all over the place, okay. And he said, I can remember him saying, well, sometimes everything looks very favorable on the ground, but in the upper atmosphere, it's not going to happen because the winds are too strong. And anything that tries to form is going to blow the top off of it. Now, he said that day in April of 2011, this index that they sort of use and make up, and use, they had never seen a number that high. And they said, we don't even know what to predict because we've never had that kind of number, that big a number. We don't know what's going to happen. We know it's going to be bad, but we can't even say what it's going to be. We've never experienced that before. So, and literally we got something that was hopefully a once-in-a-lifetime event, that we aren't going to have any more of those, because that day was incredible. The number of tornadoes, the magnitude of the tornadoes, the amount of damage. I'm trying to think. I know I've heard how many lives were lost that day, but I don't recall. It seems like it was topped 100. Do you recall? It was all up and down the state. It was it was a lot. Okay. And I can remember, not right after the storm, but we have a place up in Winston County on Smith Lake. It was my wife's parents had bought it, and then they sold it to us when they wanted to build their retirement home. And they said, you don't have children, you buy the lake cabin. Yes, ma'am. Yes, sir. So we bought it. So we were going up to see if it had sustained any damage. And in driving up there, you go through swaths where those tornadoes had come through. I mean, huge swaths, every tree down. We went by a place that had trailers for tractor-trailer trucks, rental trailers. I don't know what the name was. Swift maybe, or something like that. You've seen the Swift trucks they rent. It looked like someone had been playing dominoes with them. They just were tossed and turned all over the place. It was just, the devastation was just unbelievable. And you go through one band, then a little bit later you go through another band. And later, the next summer I think it was, or maybe that summer, we were driving to go somewhere. I think a friend of ours there was something going on at Southern Miss or something. We were driving through Tuscaloosa, and we saw just areas on the interstate where there'd be nothing on either side. Big old swaths, every tree taken down. Every one. It was just utter destruction. Okay? So, insufficient technology to connect the small and large-scale events. What's happening way up there, what's happening here, what's happening there, sometimes it's hard to connect all the dots. And that's why the models disagree, because they just don't have the data or the technology to understand the data. Mostly the data, I think. Ultimately, oceanic influences need to be better understood. That's the next chapter, the Earth's oceans, Earth's waters. The biggest part of our planet we know almost nothing about. They literally say we know more about the surface of the moon than we know about the surface of the seabed underneath our oceans, because they're really hard to study, and we don't understand all the oceanic influences. All right, that finishes the first, you might say, half of the chapter. Okay? Now we move into the second half, which is climate. Okay? Now, what is climate? Climate is the composite, meaning you put together lots and lots of data over a long period of time, larger weather patterns occurring over a number of years. Okay, not what's happening today, tomorrow, and 7-day forecast. That's weather. Climate is looking at the big picture over much larger time intervals, and you get larger, more distinct patterns. What we've had in the last couple of weeks has been anything but climate. That's been weather. We've been up to 60 or 70 degrees and down to 40 degrees in the 30s, and then back up to 60s and 70s. That's not long term. That's changing constantly. We've had winds blowing from the south, winds blowing from the north, winds blowing just about every direction, you know. That's not a pattern. That's weather. It's not climate. Now, climate is the determining factor in a bunch of things. One is the types of plants and animals at a given location. Now, this sounds bizarre, and to me it is bizarre. I did some graduate work at University of Nebraska-Lincoln. I had been further north than that, but not for any extended period of time. I was up there for, I crammed the 3-year program into 5, so I was up there for about 5 years. And during that time, I remember the first time I heard them say, we have never seen aardvarks by the side of the road in Nebraska ever before. Aardvarks are, armadillos. Armadillos. Never seen armadillos up there. And yet they began seeing them. I bet you they see them every year now. Okay? It used to be you just didn't have them. Okay? On our farm, we're plagued by fire ants. Fire ants came from Mexico or somewhere further south and made their way up. So, never seen those before. And they're a pain in the neck and a pain wherever they bite you, okay? Now, on the more beneficial side, I lived on this farm where we now have land. From the time I was 4 years old, we didn't live on the farm. We owned the farm from the time we were 4 years old until now. I mean, we've been associated with it. Reggie is here. How are we doing time-wise? Oh, yeah, we got plenty of time. Okay. And we raised cattle the whole time. And all the time that I was growing up on the farm, from age 4 until I graduated from high school, okay, I had never seen, that I recall, a cattle egret. And yet, in recent years, they're all over the place. Now, we've sold the cows now, so they're not at our farm anymore. But these were great big old birds. They look kind of like a crane or something. Beautiful, wide wingspan. They hang out around the cows because the cows attract insects. And as they graze, they stir up insects. These cow eaters are hanging around to eat the insects. And that's a really good thing, you know. They actually will sit on the cow's back and pick at flies or other things. It's a really good pest control. And it's all natural, okay? It's a very good thing. And they're beautiful birds to watch fly. They're just incredible. And up until we sold the herds, I just enjoyed getting out watching those birds. The goofy-looking things walking around, and then they just take up in groups and just fly and glide across the air. They're just beautiful to watch. Never had them before. So the types of plants and animals at a given location, that's determined by climate. These are indicators climate is a-changing, okay? The picture shown in the book, a lemon tree. Can we raise lemon trees up here? Only if you put them in the garage or somewhere else, put them inside during super cold weather and then bring them back out. My wife likes lemon trees, and we got 2. But we have them on rollers, so we can roll them into the garage when it's getting really cold, roll them back out when it's not so cold. We've had them outside most of this winter. Only a few times had them inside. So, the termites. Pecans will not grow very much north of Nebraska. I knew of one pecan tree in the whole city of Lincoln. There had to be some more because it did produce nuts. It just won't happen. The growing season isn't right for them. Okay? Whereas peonies will hardly grow down here, but they grow like crazy up there in Nebraska. So, yeah, the types of plants and animals in a given location, the climate is a real big determining factor of that. The types of houses built. Have you ever seen pictures in the Alps, say, of those chalets? The roofs are like this. Now, is that just to look pretty? They do look pretty, by the way. Is that why they build the chalets with such steep roofs? What you think? No, they build them so the snow won't sit on them. Because it snows so heavily in the Alps, if you had a flat roof, like every building on this campus, except for the Jeff Lanier building, and they just renovated that a few years ago and put a slanted roof on. But before that, all of them were flat roofs. Hey, you wouldn't have that in the Alps. All those roofs would cave in when all that snow fell on them, and it would literally cave into the roofs. So the chalets are built like that. So our roofs have to be, you know, something like this. Mostly for wind purposes, not for others. We have flat roofs here. Wouldn't happen where there's heavy snow. We don't get any snow here to speak of. It affects lifestyles, okay? It's not at all surprising to me that the best football in the U.S. is basically Southeastern Conference and some of the schools in Southwestern Conference and places like that. Why? Kids can practice all year long. It might be a little cold in the wintertime, and the coaches can't practice with them. There's rules in place. But you can be outside practicing that. Whereas, we don't have very good hockey down here, do we? No, because no one can skate at all here. You know, you have to go to special skating rinks and pay money. Whereas up in Canada, go out to any river or stream in the wintertime and you can play hockey to your heart's content. You don't have to pay a thing, okay? So, lifestyles. I mentioned sports. You could also mention just about anything else. Where are most of the golf courses? In the South. You know, they have golf courses up north, but you can get a lot more play out of them in the South. Shoot, President Trump's at Mar-a-Lago every time he can be there, you know, year-round, you know. So, yeah, it's lifestyles vary, okay, with climate. Influences. What does climate influence? it influences the shape of the landscape. That's one. The types of soil, and I think we're going to talk about these in a little more detail, and agricultural type and productivity. Now let's see if they hit those individually. Nah. So let's hit them here. Okay? Shape of the landscape. Now you say, how does climate affect the shape? Well, the prevailing winds affect it. Remember those illustrations we had? The rock that was like this, and as the winds, prevailing winds, it just eats it away and gives it a slope like that. Okay? That's one. The amount of rainfall. How much of the soil is washed away every year, you know? Do you get gullies and things being formed? Okay, types of soil. That a lot of that depends on temperature and moisture, two factors, temperature and moisture. We have both. Very high moisture, very high temperatures. Our soils are really poor soils, basically, because they're weathered so incredibly highly. Whereas up north, say Nebraska, Iowa, those kind of places, in the wintertime they have no chemical weathering going on at all. It's too cold. Down here we have chemical weather going on every month of the year. As warm and moist as it is outside, those bugs are eating up the humus, the organic material from the soil, as fast as it can fall. Okay? It's just incredible. So agricultural type and productivity, big difference. Now, the richest farmland, I think, in the world, some of it anyway, is in our Midwest. And we talked about the glaciers brought the topsoil down from Canada, melted and dropped it off here and put it back up. Wonderful, beautiful, very productive topsoil there, okay? So they can grow soybeans and corn, the rows really close together, just produce enormous crops. We can't even come close to that down here because our soils are too poor, you know? Just really bad. But you know what we can do down here they can't do up there? Double crop. My dad used to do it. My brothers did it too for years. They're out of it now. We'd plant the small grains in the fall. They grow slowly, but they grow over winter. They survive the winter. And then in early spring, they just take off and grow. You could harvest them in May. And then you can plant soybeans in the same field and harvest those in September, October, November, you know, no sweat. Well, guess what? We were double cropping. They can't do that up north. They can't even get in the fields until probably late March, early April because the soil's still frozen. There's still snow on the ground. You can't do anything with them there. So, yeah, agricultural type and productivity. We can have cows out in the field all year long. Up there, they have to have shelters for the cows in the coldest weather because they would die, you know, if they were exposed to that. So, yeah, agricultural type and productivity. So let's look at the major climate groups. Two primary factors that determine this. One is the intensity of incoming solar radiation, okay? And here's Melanie. Okay. Intensity of incoming solar radiation. Now this is, we've talked about many times, basically near the equator, you have a band between 23.5 degrees north and 23.5 degrees south. Sometimes during the year, the sun's directly overhead, everywhere in there, or somewhere in there, and that's in the tropics. That's what we call that band there. That has the most direct incoming, most intense incoming solar radiation. It's determined by the angle of incidence. Tell you I'll be the sun again. If I turn this, the equator is always in sight, and that band is getting direct radiation from you as you stare at it, right? Up here, it's more oblique. This is where we live. Up here, hardly any at all. Even when it's facing the sun, the angle is really great. Okay? So it's determined by the angle of incidence. Now, this also affects the number of daylight hours. Okay? Near the equator, again in the tropics, you have fairly uniform number of daylight hours year-round. We saw that in the second lab. 12 hours, 12 hours, 12 hours, anywhere near the equator. Okay? But the further north you go, or the further south you go, the more the discrepancy is. And we did it for where we live, I believe, and found out something like 14 hours of daylight in the summertime or something like that, and 10 hours of darkness, whereas in the wintertime, the coldest part of wintertime, you have reverse of that, 10 hours of daylight and 14 hours of darkness, okay? Whereas on the North Pole or anywhere up there, they'll have all day of no sun never rising, and then other times of the year all day when it never sets, okay? The spring and fall, everybody is 24, 24. That's number of daylight hours, okay? The tilt of the Earth's rotation axis, that's what causes this discrepancy. We've been talking about that. The equatorial regions receive more direct solar radiation, that's what we said. The intensity changes on a yearly basis. Now that statement, I think they mean the intensity changes on a seasonal basis. That makes more sense. In a year, you have different intensities, especially when you're in the temperate and polar areas. Big differences. In the equatorial areas, it's almost constant year-round. Now, what may not be constant there is the rainfall, but we're not talking about that now. We're talking about radiation from the sun. Okay? The number of daylights varies annually. Number of daylight hours varies annually. And again, that's sort of a weird statement. What it means is, over the course of a year, the number of daylight hours vary. So I guess that's what they mean annually. It's sort of, the way that reads, it almost like, well, this year we'll have this many, that year we'll have a different number. That's not what it means. Over the course of a year, the number of daylight hours vary, again, seasonally. Okay. Did y'all get that? Was there anyone still writing that one? Okay. I can go back if you need. So, what are we talking about? Climate and latitude. Okay? In the low latitudes, that's the portions near the equator, you have high solar radiation. The yearly variation is pretty small, okay? So the temperatures are uniform and therefore fairly uniformly high. Now, let me get back to a weather type issue. I only went one time, I think, but the pastor of our church was sponsoring a book study, and the study, I can't remember, it may have been Rick Warren's Purpose-Driven Life or something like that. Anyway, the first chapter was sort of a general thing, and people started talking, there was a lot of people there, and they started talking about, well, I don't know why this and so happens, why we have these terrible events, like weather events and stuff. Why does this happen? That doesn't have to happen. Why do we have to have hurricanes? Well, it happened to be Jerry Tracy, at least that night, was there in the group. He said, well, wait a minute. We have to have them. We have to have hurricanes. And why is that? Because you get so much direct radiation from the sun in the tropics that if you did not have something to haul that energy away, you're going to have some pretty serious problems. Very serious. Catastrophic problems. What the hurricanes do, they take the energy from near the equator and move it up into the northern latitudes. And the southern latitudes if you're down there. They're in the north. And that's exactly what's happening here. It's hauling them in up there. If you didn't have that, the northern part of the globe and the southern part of the globe would be so incredibly frigidly cold, a lot of things couldn't even survive. And, on the other hand, around the equator, you would have such incredibly intense hot temperatures that a lot of things couldn't survive. So, you have to have hurricanes to do that. So, when I say temperature is uniformly high, one thing that keeps it from getting too high is the fact that hurricanes move the energy away. Okay? That I should have mentioned back in weather other than climate. In the middle latitudes, that's where we live, we have higher solar radiation during one part of the year. Well, that's the part when we're facing the sun, we're tilted toward the sun, we're going to get pretty intense radiation then. Okay? Not as intense as they get at the equator, but still fairly intense. Okay? Overall temperatures are lower than they are in the tropics overall, but they have greater variation than the low latitudes. Okay? In other words, I can remember hearing someone griping, which I couldn't believe, about the weather in Hawaii, that it was just so boring. It was always in the 60s and 70s. Very seldom even made it to the 80s. Give me that any time of day, okay? Now, I guess if you live there years on end, you might get a little bored with it. But I'd rather be bored that way than bored shoveling snow, okay? I'm a southerner, okay? Then when you get to the high altitudes, this is way north or south. Here you have the maximum amount of radiation is only during one part of the year. Like when the North Pole is facing the sun, then they get solar radiation. It's not a lot because the angle of incidence is so great that you don't get very much, but you do get it almost full time then. And another part of the year, you're not going to get a bit. None. Not a zero, zilch. Not a bit. That creates some huge variations. Okay? So the maximum amount of radiation during one part of the year, none in the other. Overall temperatures are lowest, but with the widest variation. I mean, maybe in the summertime they might get up in some areas into the 40s, 50s, maybe 60s, what we consider a cold day out there today. But in the wintertime, minus 45, minus 50. Don't even get me close to that, okay? I don't want to be there. That is huge variation of ranges of temperature, okay? Now here's a picture that's showing that, and this is the only thing wrong with this picture, sort of, is it doesn't show the tilt of the Earth. But I guess it's okay. We could be looking at an angle that we can't see the tilt. Maybe we are because you see the longitude lines going to a point up there. So the North Pole is slightly tilted this way. South Pole is slightly tilted that way. Okay. My eyes are burning. I don't think I drank enough for lunch today. So anyway. Here are the low latitudes. These are between the Tropic of Capricorn at 23.5 degrees south, Tropic of Cancer, 23.5 degrees north. Somewhere every day, a band within this range has direct solar radiation. Direct solar radiation. Right on the money. Every day of the year, some part of this is getting direct solar radiation. The middle latitudes where we live, everything's at an angle. Everything. Even when we're directly facing the sun, it still has an angle to it. Okay? That's less intense radiation because of that angle that it has. And in the higher latitudes, and this is defined by the middle latitudes are between the Tropic of Cancer, 23.5 degrees north, to the Arctic Circle, 63.5 degrees north, or between Tropic of Capricorn, 23.5 degrees north, to the Antarctic Circle, which is, I said north, this is south, 66.5 degrees south. Inside that Arctic Circle, look at that angle of incidence. So much of this is reflected off the surface That's why they don't absorb a lot of heat. Okay? And then sometimes of the year, it's actually pointed away from the sun. You get zero because none of this, all this band here will be below the Arctic Circle there all year round. Okay. Not all year round. Sometime during the year. Okay. Okay, that previous slide was talking about climate and latitude. Now let's look at climate zones. And it almost sounds like we're going over the same stuff, and it is related, but they sort of have different names, and that's kind of important. Defined in terms of yearly temperature ranges. These are your climate zones. Now, they have several. Okay? Three big ones here. Tropical climate zone. That's the tropics, in between the Tropic of Cancer and the Tropic of Capricorn. 23.5 degrees north, 23.5 degrees south. Near the equator. It receives the most solar radiation, hot. All year round, it's hot. Okay? Some places not as hot as others, but still that. Then go to the extreme near the poles, the polar climate zones. Least solar radiation, anytime during the year. Cold, cold, cold. All year, anytime. But sometimes way colder than others. Constant daylight part of the summer, constant darkness part of the winter. Now, if you're right on the Arctic Circle, that only happens once in the summer and once in the winter. You'll have total radiation. All the rest of it, you'll have some period that you have some radiation. All right, the temperate climate zone, that's where we live. That's the biggest one. This is intermediate between the other two. Okay, that's not saying a lot. Now, rainfall patterns shift seasonally. Where we live, this is kind of true, but not totally. We have fairly uniform rainfall patterns. Now, this year has been exceptional, and when I say this year, the last 12 months. I don't know if I can recall, certainly during my adult lifetime, any year we've had more rain than we've had this year. I mean, last summer, it never was a drought condition that I can recall, and maybe for a brief period of time, I don't know, I don't even think there was any time that we had long enough periods of sustained drought for it to be considered a drought, at least here in the southeast. Now, California and some places like that, they probably did, but they had all these severe wildfires and stuff. But we just had a incredibly wet, probably more than a year. All right, so that's the temperate climate zone, intermediate between the two. Now, this statement, rainfall pattern shifts seasonably. That's quite a statement. And the patterns vary like crazy. And they do shift pretty crazily too. Does anyone know, on average, the state of Alabama's driest month of the year? What would you say if I asked you what, on average, Alabama's driest month of the year was? Anyone make a guess? Hazard a guess. July. That would be a pretty good guess, wouldn't it? Because it seems to be when it's hottest and that kind of thing. Probably I'm sure there's some places it is, okay? But in reality, I've got weather information back there. it shows it's October. What? October is generally, on average, our driest month of the year. It's not a lot different from July, but it's quite a bit. Why would we say July or August? Why would we notice that? It's also hot then. Plants are at their peaks then. And when we have a drought then, everything suffers big time. But guess what October is? It's a part of the year you're just heading toward winter. There's not a lot of plants out there suffering too much. If they were suffering, it may be more from cold than it would be from drought. Okay? So, now, let's go to other parts of the world, not Alabama. Y'all ever heard the concept monsoon? And by the way, I saw Seth come in, but I forgot to mark you present. Who else came in late? I got Melanie. Anyone since her? Okay. Sorry, I just realized when I saw Seth over there. I saw you walk in. I was in the middle of something. Anyone ever heard the term monsoon? Anybody? Yeah. Okay. Now, in many places of the world, we have friends who are missionaries down in Cameroon. They're not there now because there's a huge civil war going on there. But that's where they've been for most of their adult lives recently. And they don't talk about winter or spring or fall or summer because they're down near the equator. That doesn't matter. They talk about the dry season and the wet season. That's how those are their seasons. Rainfall pattern shift seasonally. Okay? Seasonally. And that's what a monsoon is that time of year when you get lots of rain, and then there's other times of year you get hardly any. Fortunately, we here in the Southeast don't have that kind of activity. We have it to a small extent, I would say. Feels like February we're in a monsoon, but that's not normal. We've had some years where we had very dry winters, and those really bode poorly for agriculture because if the soil doesn't have much water holding capacity in the wintertime, the next summer, July, when it gets as hot as it does, plants cannot get the water they need. So rainfall patterns shift seasonally. Now, what you saw before in a figure like this shows really sharp lines of demarcation. These are the tropics, these are the equator, this is the Antarctic, in the Arctic Circle, these are that, everything. Real life isn't that abrupt, okay? This picture is closer to what we have in reality, okay? Here are the tropics here, the dotted lines here. The actual tropical climates, though, are inside these lines like this. Part of it depends on how much is land and how much is sea. But a lot of the rest of it depends on other things, prevailing winds, ocean currents, those kinds of things. So here, this part of the ocean, even though it's in the tropics, acts more like temperate. Whereas here, even though this is barely in the temperate region, and over here, it acts more like the tropics, okay? Here, it's in the temperate region, but it's more like the tropics. Up here, in the temperate region, in the tropical region, but it acts more like a temperate, okay? Let's move on to the polar areas. And down here, it's really distinct. There's the Antarctic Circle here. And let the polar regions go way up to here, including the tip of South America. That's called Cape Horn, I believe it is, the tip of South America. They say there is no worse weather in the world than around Cape Horn. It's stormy, it's windy, it's miserable, and yet that's where ships, sailing ships, used to have to go around here to get from Europe to the Far East, from U.S. to even from East Coast to West Coast, you had to go through there. And that was a pretty miserable point, okay? It acts like polar climate there, even though it wasn't in the polar region earlier, okay? So you get all sorts of patterns like this. A little less distinctive up north, but here in the Hudson Bay, you get way down into Hudson Bay with still polar conditions, even though the line is up here 66.5 degrees north, was where you usually think of the polar region. So, okay. Now we're back to sharp lines, and these don't make any sense. The waving lines make a lot more sense. What we're talking about here now is not temperature, but wetness, okay? That last little check mark there. And this admittedly doesn't make a lot of sense here. They have very wet, basically near the equator, and then suddenly it jumps up here. You know it doesn't suddenly jump up there. It is gradual. It's a lot more like what we saw in the previous slide, like that, okay? But part of what's causing that is down here you have the Andes Mountains, and it doesn't let the moisture inland. So that's why it's not wet there, okay? It's wet near the equator, and it's wet out here, but it's cooler here, and that's because of ocean current. So there's all sorts of things that are influenced here. And this, for there to be this big a jump here, that makes no sense. That covers thousands of miles there, okay? Why would it be a jump like this? Sure, there's a change, but it's a gradual thing like that. Up here we have almost as bad, not quite as bad, a jump here. But we're in the wet area here, and then it moves into dry right up here. Now, my younger brothers say, yeah, that's right where our farm is. We were drier than anybody else in the state of Georgia. And that was almost true. But see, the Gulf of Mexico is the big supplier of moisture here. You know that out here there's Mojave Desert. That's not wet. This is a gross general map, so you can't really do too much with it. But in general, it's very wet around the equator. There's a patch north and south of there where it's rather dry. And then we're in the wet area north and south of that. We're north of it. And then you get the cold area in the extremes. Okay. Running out of juice. Okay. Now, let's move now to regional climate influence. And they have several really neat pictures in the book. I've already pointed out a few of them. The computer room that's making the weather forecast, it's a pretty old looking picture there, but it's pretty complicated. The lemon trees, mostly in tropical areas or subtropical. They show some of the plant life. Goodness, my throat's going on me. In tropical area, and then they show polar climates where the antelope or whatever this thing, the great big herds of those live. And they have to do a lot of grazing to get what they need. But here's the other thing about how plants and things adapt. That little bit of grazing they have there can sustain them better because typically the nutrient value in those grasses is very, very high. Okay? whereas the grasses down here in the southeast, a lot of them are just totally carbohydrates, okay? The cattle, you'll sometimes see them just eating and eating and eating and still not looking that good. That's because our grasses just don't have that much nutrition. They're just carbohydrates. Now, I had a friend in Nebraska, her mom and she had a ranch out there in the sand hills. And I said, well, don't you feed a lot of alfalfa hay? Oh, no. We would die for alfalfa hay here because it's so rich in protein. It would put the muscle on the cattle. And she said, oh, no, give us that high calorie because we need our animals to keep warm in the winter. We don't need them putting on muscle. They need fat layers. So it was a completely different attitude. The grasses we have down here are high carbohydrates. We want them to have more protein. The ones they had up there were high protein. They wanted more carbohydrates. Farmers are never happy, okay? These cattle, or the antelope or whatever they are grazing out there, they're probably getting pretty good nutrition, even though they don't have a lot to eat on, it appears. All right. So regional climate influences, on the slide it's influence, here it's influence, starting on page 590. A couple of these figures you've already seen. 4 major factors, okay, on the regional climatic influences. 4 factors. 1 is altitude. Yeah, that's pretty important, okay? Cole made it in under the bell, okay? Turned out being a fairly well-attended class today. It didn't look like it to begin with, but now it's getting that way. Altitude is the higher altitude air, higher altitude you are, okay, the air radiates more energy back into space than down at low altitudes. Now, why is that? Because the atmosphere acts like a blanket, okay? And the thicker the atmosphere is, so at the lower altitudes, you got more blanket above you, okay? And there's more distance the energy has to go to get back out of. But when you're at a high altitude, you've gone through a lot of the thicker part of the atmosphere. You're in the thinner part now, and it's much easier for you to lose that energy back into space. So that's why tops of mountains can be snow covered in the summertime when it's very pleasant at the bottom of the mountain. But at the top, because the altitude is much greater, you still got snow on it. Now, altitude then mountains. Aren't they the top same thing? Well, kind of. But remember we talked about the Himalayas, okay, down here, Nepal, okay, northern India, Tibet, those areas. Everything's high there. So Mount Everest is the tallest mountain on the planet, but it doesn't stick up above ground level as tall as you would think. Mount Kilimanjaro in Africa, everything's real low there, and it just shoots up like crazy. So it's a taller mountain. Remember y'all did it for the Devil's Tower National Monument. Its elevation, that's its altitude, was 5,000 or some feet or something like that, but its distance above the ground level was only 800 to 1,000 feet because everything was at a higher elevation there. So altitude would be, even the surrounding areas, the mountains was how much sticks up above that. And certainly your cooler air at the higher altitude, we were talking about that. Now here is an important statement, and I've seen it a couple of different ways, and this is the best way. The upwind slopes receive more precipitation, the downwind slopes less. Here's what they're talking about. Picture our west coast. Now if you run your finger over here, you'll find there's a series of mountain ranges. There's the Cascade Mountains in the Pacific Northwest. There's the Sierra Nevadas in the central western area into the southwest area, and then you go on down. It's even more distinct down here, and I just mentioned it to you, in South America with the Andes. That's a huge rhythmic mountain. And they're formed because of the subduction and the volcanic activity that you have there. Well, up here the prevailing winds are westerly because we're up in the temperate area. The prevailing winds westerly. They hit the mountains coming off the ocean, carrying plenty of moisture, hit the mountains and the moisture falls off. So the upwind slopes receive more precipitation. Once you get on the other side of the mountain, all the precipitation's gone. The downwind slopes are drier. The state of Washington, there's not many wetter cities in the U.S. than Seattle. It just rains there a lot, okay? A lot. For like now, it just, they used to make jokes on, oh, we may have a little sun this week, that'll be Thursday afternoon. We'll see the sun, because it's just always wet. But you go across the mountains in eastern Washington, it's really, really dry. Really, really dry. The only agriculture they have there is irrigated, okay, because it's so dry. The mountains block that. So the upwind slopes receive the precipitation because it gets cooler as you go up. It rains and rains and runs downhill. Okay, on the downwind slopes, less precipitation. Okay. Now, I don't know if it's a statement in the book or somewhere. They're talking about the U.S., and they'll say the western slopes have greater precipitation, the eastern slopes less. That's true here, but it wouldn't be true, say, in the equatorial region. It wouldn't, there's different parts of the globe that wouldn't necessarily be true. And then when you have something like the Gulf of Mexico down here that's supplying the moisture this way, that doesn't make any sense at all. Only that part there. But this guy lived in the West, so that's why he did that. Phrase it that way. Now, another regional climate influences are large bodies of water. Okay? Now, we haven't talked about this specifically, but I think I have mentioned it before. Do you know what specific heat is? The amount is the ability of a material, if I can phrase this right, how much heat it takes to raise the temperature of a given amount of material, a given temperature range. Of all the materials on the earth, native, natural materials on the earth, water has just about the highest specific heat of any of them. Water, this most common material, highest specific heat of anything. What that means, that water, because it takes more energy to warm it up, that's why I remember I gave the illustration driving to the beach. It gets warmer and warmer because you're going south, usually hotter in Montgomery than it is in Birmingham. Driving south and it just keeps getting warmer. Suddenly you get near the beach and it feels cooler. The reason is water has a very high specific heat. Land, very low specific heat. Water about 1, land about 0.2. 1/5 the specific heat of water, approximately. Okay? So the water moderates temperature changes. If you do that same trip in the wintertime and go south, of course you're going to have slightly warmer temperatures as you go south. But then when you get to the beach type area, it's even warmer. Montgomery will be quite a bit colder in the wintertime than, Orange Beach, okay? And the reason for that is all that heat the water absorbed in the summertime, it's giving it up slowly in the wintertime. So our favorite time, my favorite time, I think my wife too, of going to the beach would be October and November. Number one, you don't have the crowds. Number two, it's just really nice weather then. It's not hot, sticky, and everything else. I don't like lying out in the sun anyway. Okay, and then the fourth big factor is ocean currents. Well, I already said large bodies of water. So the other two related to mountains and elevation. These two are related to things. But you see, it's not just oceans. Gulf of Mexico is a large body of water. That's our major weather producer, okay, or climate influencer. Okay, but even the Great Lakes, people in Buffalo and Rochester, those kinds of areas, they'll quite often have snow in the wintertime, and they have a special name for it. Lake effect snow. Water has come up, been evaporated off the Great Lakes, and then gotten into the atmosphere, frozen, and makes snow. That's not coming from the Pacific, that's coming from the Great Lakes, okay? Hudson Bay, Gulf of Mexico, okay? Those are large bodies of water that can moderate temperature change. But then ocean currents, they can do all sorts of weird things. And we'll do more of this in the next chapter, but here's one of the things. In fact, they may even show it here. I may not have to point it out there. Yeah, here we got it. Our major ocean current for us is what we call the Gulf Stream. The Gulf Stream, all this tropical area, see there's the Tropic of Cancer right there. So this is tropical moisture, temperatures here, really warm. That comes up into the Gulf of Mexico, keeping it nice and warm. But then that continues the process of moving up here. It keeps every one of the U.S. seaports on the East Coast free of ice all year long. You can go to other areas like poor old Canada. Now they're further north, but this is a Labrador current. It's coming down from very cold, close to Arctic waters here, and it freezes over much of Canada's East Coast ports. Poor Canada. Yeah, they're further north, so you expect a little of that, but because of the ocean currents, they have unusually cold harbors. We have unusually warm harbors, okay? Not very fair. Now, out on the west coast, it's a little different. Here is the North Pacific current. They're coming from about the same region, okay? The North Pacific current comes up and warms up British Columbia. They have open ports all year long. East Coast, frozen. And they're further south, all year long. Most of Alaska's, that little band of Alaska that comes out, stays free. In fact, most of these ports are free of ice all year long. But Southern California, where it should be really warm, you can hardly go to the beach there in the summertime. You can, but most people wear wetsuits. What? Wetsuits because the water is so cold, because this California current is coming from northern waters bending down this way. San Diego is very pleasant temperature just about year-round because of this California current. It doesn't get all that hot in the summertime, most of the time, and it stays moderately warm in the wintertime as well because it's so far south. But you don't see as many people. You see more people on the beach in Long Island and Massachusetts and New Jersey enjoying the summer in swim trunks than you'd see in California because it's so cold there. The water's so cold. Way down south in Southern California. Okay. So the ocean currents can bring warm water to cold areas, and they can bring cold water to warmer areas. Okay. Very different from that of land. Now, this Gulf Stream doesn't just affect us this way. It bends on around and keeps England free, too. England's pretty far north, okay? And as far north as England is, it should have frozen harbors in the wintertime. It doesn't. The North Stream keeps them. That's why England could have been Britannia, the queen of the oceans. They never froze over in the wintertime. And as far north as they are, they should have. For Canada here, further south than that, they would be frozen. England would be free. Okay. And a lot of Europe is affected by the Gulf Stream, too. So it's not just us. Europe is benefited, too. You don't see it here, but we'll see it in the next chapter. There's also some currents down here that keep Siberia unusually cold. Well, Siberia, if I don't feel too sorry for it. Okay. Now, how do we go about describing climates. This is the blurb that starts on page 592. Describing climates. Okay. Now, I tried to point this out on a couple of the illustrations we've had before. Those illustrations that show the sharp boundaries, they're not realistic. Problems are there are no sharp boundaries. You can't say this is this and that's that because it's an integrate. There's always an integrate. No two places have exactly the same climate. Now, we'll claim that they have like climates. For instance, the San Francisco Bay Area is quite often said to be a Mediterranean climate. Very similar in its climate to the Mediterranean Sea, but different. There are very sharp differences there, but they're fairly close in something. They grow great grapes in both places, okay? The wines coming out of Italy and France and stuff are wonderful, so are the ones coming out of California and places like that. But no two places have exactly the same climate. A description of North America climate zones follows, and this is one of the last, we're getting near the end of the slide set here, and this figure that they're going to show here is also in your book on page 593. The table describing it, parts of it anyway, is on 592. I don't think they show the table as much in the slides as they do the thing. Okay. We're not quite there yet. Let me see. Yep, there it is. Okay. Major climate zones. Now, if this sounds like it's similar to what we were doing before when we were talking about air masses, we use some of these same terms or something pretty close to it. So major climate zones, marine climate. That means you're near the ocean or a big body of water. Okay, it doesn't have to be an ocean, but near a big body of water. This is influenced by the air masses from the ocean. So what we're calling marine air masses, that affects the marine climate zone. Air masses we were talking about back then for weather purposes. Now we're talking about overall long-term climate purposes. You have continental climates. These are far from the ocean, influenced mostly by air masses from large land areas. They could be large northern or cold land areas or from large hot land areas. Generally, they're fairly dry producing climates, but the temperatures are going to be the very big changes. These are wet type climate producer zones here, but it could also be from northern or southern, okay, or cold or hot. Other classifications: arid, meaning very, very dry. Semi-arid, not quite as dry, but still drier than normal. Humid, that's what we have, humid, okay? And then there's various other ones. All right, and here's the map. Now this is small. Your book almost gives you a bigger view of it than even the projection here does, but it's exactly the same figure. I'll try to read it from here. I'll have to go back and look at some of the words there. All right, starting with polar, way up there. Notice, remember we said this isn't always within the Arctic Circle. Yeah, up here you're within the Arctic Circle, down here you're not. You're way far from the Arctic Circle. The Arctic Circle cuts through Greenland, but all of it is considered polar. This part of Canada is considered polar, even though it's well below the Arctic Circle. Okay? Now, humid, continental, subarctic. That's this band here. Okay? It's humid. They get plenty of moisture and stuff. It's continental, which you wouldn't think has much moisture, but it's subarctic. Now, all those tie together in a certain way. Because it's so cold, they don't have a lot of evaporative loss. We may get a lot more water down here than they do, but we may be drier than they are because our water evaporates away, especially in the summertime, whereas theirs doesn't because they're much colder. They don't have as much evapotranspiration, they call it. Okay? Humid continental mid-latitudes. That's this one here. Okay? Now, part of that humidity is contributed by the Great Lakes. Okay? Those are large bodies of water not associated with the oceans. Can't really tell you why this is. Well, there's some lakes in here, but this is still humid continental mid-latitudes. Probably because, again, you have pretty cool temperatures, so they don't have a lot of evaporative losses. Okay? Humid continental low latitude, I think that says, and that's this one. Hey, that's fortunate for us. This is our farm belt. Really great agriculture here. Good amounts of moisture, not great, but good amounts of moisture, and lots of good production here. What we're called here is humid subtropical. This is definitely subtropical weather, not mid-latitude weather, okay, even though we are in the mid-latitudes. Now, what a huge line of demarcation here. What do you reckon causes that? Mountain range. This is almost, not quite, but influenced largely by the Rocky Mountains. Okay? That's about where that is. But even more so, the Gulf of Mexico. This is providing all the moisture here. This is on the downwind side of the mountains, so they just don't have the moisture here because this curves up and gets blown off of them. So that keeps this part humid. This part's dry because they're on the wrong side of the mountain. Okay, they're on the downwind side. So the Rockies don't come this far, but their influence goes that far. Okay, I jumped over there. Humid subtropical. This is tropical wet. Now this blue is this one right here. That's the Yucatan Peninsula, it's called. That's the one part of Mexico that is wet, 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 wet. You think of Mexico, I think of Mexico as being almost a desert country, and much of it is, but that part is not. That is a very wet area, very tropical wet area, tropical wet. Tropical with seasonal wet dry. That's what it says. Seasonal wet dry. I knew it was something seasonal, but wet dry is what that says. That's this part here, this green down here, including Cuba and Hispaniola and Puerto Rico. I think this may be Jamaica here. Okay. This is your monsoonal type. It's tropical, but sometimes wet, sometimes dry. Usually about 6 months of each. Don't have fall, spring, summer, winter. They have wet season and dry season. Okay? That's a lot of Central America is that way. Okay? Then they have semi-arid. Okay, they seem like they skipped some in there. Here's the semi-arid. And this is on the downwind side of the Rocky Mountains. Right next to very humid subtropical. Now the lines are not this big. Like I said, there's that was on the previous slide. There are no sharp boundaries here, but it grades that pretty directly. Okay, that's the semi-arid. These are the deserts, and look, poor old Mexico, just around. Now this to me is the most incredible part. This whole Yucatan Peninsula here, look at the size of that. It's counted desert. And what is it? It's surrounded on two sides by water, actually three sides by water. Why is that a desert? It seems like that would be more like it is down here. There's just something about it that's not. It's influenced by more from the land than it is from the ocean. This is marine. That's this part here. And that's pretty incredible. It would go up all that much of Alaska and northern Canada, British Columbia, Victoria Island, Vancouver, Seattle, of course, and Portland, and Northern California. These are marine type climates here. They benefit from the ocean. Okay? The Mediterranean climate, that's what I was talking about before. There's San Francisco Bay right there. Napa Valley is up in here, and the other Imperial Valley, I think some of the other valleys are there. Just Mediterranean. Very close to what you see in the Mediterranean. Europe, at least part of the Mediterranean, maybe a little bit in the African part too. And then these are the highlands. They're just mountain areas. This again was the Cascades, the Sierra Nevadas, and the Rocky Mountains. It's hard to classify them as a climate zone because they're rocks. Okay, who cares what the rocks are? So those are just highlands. And they have more of these down here. And this is what contributes to the seasonal, because the highlands are blocking the moisture coming in. Okay, and some more highlands here. If you went on into South America, the Andes are huge highland area. All right, kind of makes sense? Blah, blah, blah. Okay. Now, let's talk about some local climates. Now, there are a few examples here. There's not too many in this chapter. And its following table lists average monthly temperature data, total monthly precipitation for a location in North America. In which major climate zone would this location be? So if you look at that, the temperatures get way below freezing. Nothing near us, okay? In fact, January, February, March, April, May, and back into October, November, December, January, February, March, April, May, average temperature is below freezing. Not the coldest temperature, the average temperature. That means February, just about all the time. That has to be somewhere way up north. So I'm going to guess humid continental subarctic. I don't know if that's the case, but that would be my guess. Oh, and I didn't mention Hawaii. Let's go back. Hawaii is here, and you see Hawaii, it's not up here. Hawaii is down here somewhere. Oh, down here somewhere. So here is the Tropic of Cancer. It goes right above northern Cuba, but it's not into the U.S. here. It goes along here. Somewhere way out here, Hawaii is down there. It's south of the Tropic of Cancer. It's totally tropical. So it would be this tropical with seasonally wet, dry. And believe it or not, they do have a dry season. They're surrounded by water too, but they're tropical, wet, dry. I think that's that color. It looks like that's the color. I don't think that's the humid. So no, that would be not. Seasonally wet, dry. Okay, meant to say that before. Okay, so I was looking at this. I would say that looks like that would have to be humid continental subarctic. Could be mid-latitudes, but I don't think so. What do they say? Oh, that's a polar climate. Even worse than I thought. That would be even further up. That's the white, the polar climate. Okay. There's no sharp boundaries. The next example, following table lists the monthly temperature data and annual precipitation data for a city in North America. Which major climate zone is that one located? And see here, none of the average temperature, none of them are below freezing. Now, there are a few that are 4.5 and 4.2 degrees Celsius. That's just above freezing, but, you know, that's not there. Look at the rainfall, precipitation. Goodness, that several months are in the hundreds of millimeters, whereas the other one, you never got more than 40 millimeters, okay? So that, I think, would have to be the humid subtropical, that's where we live. Humid subtropical, and that's what they have too. All right. Major climate zones. Local climates. This begins on page 594. And this is just one slide, and it sort of hits a lot of stuff. You can get down to microclimates, a local pattern in climate. And I believe in the book this could even be, oh yeah, here's where it says it, can be associated with a single tree. So they have this sort of put together in weird ways. The microclimate, I think, should go with this one. But I guess that's okay. It can be associated with a large city, which is the heat island effect. And I think I talked about this last time, didn't I? Driving from here in the wintertime, back in December, driving from here home, I could see the temperature change big time. Even though I was going north and east, which should be getting cooler, as I got closer to Birmingham, the temperature went up because of the heat island or heat dome effect of the city. Now, Bessemer had a little bit, and maybe Fairfield and Inslee just very, very slight effect, but most of it was Birmingham. The buildings, the pavement absorb and emit solar radiation differently from natural vegetation and other landscapes. And there, yeah, don't think you quite made it. We are into lab time, aren't we? But here we have Corey. Didn't find you. All right. Now, the bad news today is, of course, we don't have lab time. We had several labs in a row with tests and had short class times, and today we pay the piper for it and have class basically all day today. So I think it is time, and maybe a good time. Let me get this slide done, and then we'll go in. Let's see. Yeah. So local climate, let's finish this one. Buildings, pavement, absorb and emit solar radiation far differently from natural vegetation and landscapes. Not just that. I think there's also things like cars and industry and buildings where they're heating, their air conditioning and stuff. They're changing microclimate-wise little amounts too. Now, they say it can be associated with a large city, or it can be associated with a single tree. Lichens and moss grow on one side, but not on the other. They typically grow on the northern side because that's the cooler side, okay? The moisture hangs around better. The southern side dries out too much for them, so they wouldn't grow there. However, other things like moss would grow more on the southern side because it needs the solar radiation. So anything that needs the sun will grow on the southern side because it gets direct sun. Anything that's depending mostly on moisture will grow on the northern side in certain areas. In other areas, you may not have that because the northern side may be too cold for anything to grow, and you have all the vegetation on the south side. So everything varies with the local climate. Okay. Now, before we get to climate change, which is 23.4, let me mark the roll again. Zarya is here. Okay. Marcus, we haven't seen in a very long time. Rod is still here. Gavin came in earlier, but he's not here now. Bertram didn't make it in at all today. Melanie is still here. Samaya is still here. Corey is still here. Corey, yeah. Right. There. Right. Yeah, you just came in. No, I marked you. Yeah. Okay. Thomas Earl is still. I'm off here somehow. That's what it is. I marked you on one. Okay, got it. Thomas Earl's still here. Derek Holt, I've never seen. He came the first day of class, signed in, Never have seen him since. Seth is still here. Wait, I'm off again. Well, I was doing all that talking about Derek and marked him present. Okay. Seth is still here. Rashad hasn't made it in today. Michaela hasn't made it in today.
No, she had to go to work today.
She had what?
She had to go to work.
Oh, I see. Okay. Cole is still here. Reggie's still here. Mostly, I guess. Diego's still here. I've gotten off again here somehow. Patel, skip Patel. Okay. You're still here too. And Videsha's still here. Okay. Now, before we start climate change, this is a pretty decent time to take a break. You want to take one or just keep on trucking? What you say?
I'd like a break.
I would too. So let's take a break. I'll pause the recorder. Now this is, I think, the last section in the chapter. Okay? And this is climate change. Now these are big topics these days. There's a lot more controversy, I think, than should be. Of course, anytime you have 3 scientists in a room, you have at least 4 opinions, okay? So you expect there to be a variety of concepts on it, you know. But, well, we'll get into that. I will say this. I feel like this author, at least at the time of this printing, type or copyright or whatever, seemed to me to be somewhat skeptical. Okay? From what I've read of his new edition, which we don't have, it sounds like he's coming around to it a bit more. But that was just a blur. But anyway, we'll see. Climate change is a departure from the expected average pattern of climate for a region of time. And I really don't like that phrase there. Time doesn't have regions. I mean, that for a period of time or something like that would make more sense for a region of time, unless they meant for a region and time or something like that. But a region of time just doesn't make a whole lot of sense. Now, I think I've sort of illustrated you before using the wall, and this has just been really gross too. If that was the formation of the Earth, and that was when we currently are now, mankind has only been on the planet a very small part of that time. For a long time, there was nothing much here. We were molten, hot rock, and stuff. Nothing could have lived here. And that lasted for quite a while. And then there were times when things were settling out and plants were getting established. And that had to happen a long time before animals got established. And then once animals here, different types of animals and stuff. And then sometime or another, man came onto the picture. Now, how long ago, I don't know exactly. And even on our wall, I don't know. But I will say this. We've been, I can use this term, civilized enough to be collecting data for only a very small period of time. Okay, very small period of time. So most of the time that the planet's been around, we haven't gotten data because we either weren't here to get it or weren't sophisticated enough to get the data. So that's why it says proxy data is used to infer past climate conditions. Now, what would be proxy data? Well, part of that would be going down to the Antarctic or the Arctic regions and drilling down and getting cores of ice samples, core samples of ice. Okay, and that is going backward in time when the ice was there, and you can measure things like the amount of carbon dioxide content, the amount of organic compound content, the amount of oxygen content, all these various things, and you can infer from what you find there temperatures, okay? The way the ice froze and melted and froze and refroze and stuff like this. You can infer temperatures from that. The type of microorganisms that you found left over there. You can infer temperatures from that. So that's what they mean proxy data. No one was there with a thermometer, okay? You don't know what the temperatures were, but you can see what kind of microbiological life was there, what type of slightly more advanced life, plants, animals, things like this, insects, whatever, and you can infer what the temperatures probably were. So for a long time, now we were here certainly in 1000 AD, but this is the time we weren't really all that sophisticated. We didn't even, I'm going to hazard a guess here. Around 1000 AD, we probably weren't even sure that there were people over in China, okay, because we didn't have Marco Polo go until sometime after that. So there was data collected. There weren't data available, We didn't have means of collection. We didn't have means of storage, So for a long period of time, we're using proxy data. Now, this is just AD, okay? We're not even counting BC, okay? BC, this goes way back, and then before we were even here. So we just don't have a lot, okay? So, but we noticed here from year, this looks like maybe around 900 AD to present, 2000, or not present, 2000 AD. It looks like we've been sort of through a little more than one cycle of temperatures. Now, this is based on these proxy data here. We don't have any good data there, but just what we've been able to put together. Now, more than likely, this would have looked like, this part should look like that if we would have had daily or annual temperatures to get. We didn't have it. So this is a smooth curve. If this had been collected like this, this would have been a smooth curve. But here's the part that I don't think, he says here, according to the proxy data, Earth has experienced a period of warming and a period of cooling over the past 1,000 years, from 1,000 to 2,000. Warming here and here, cooling there. And he's sort of inferring here that this is normal. Of course you have climate change. Things get cooler, things get warmer. Okay. A little bit of a timeout here. Other people will argue, you had the ice ages. Well, when were the ice ages? They weren't in the 80s. They were BCs. They were way back in the BCs, okay? We haven't had one of those, and there were at least 4 of them way back then. I don't know how far apart they were, but there were 4 different ice ages I think I've read or heard about. So, goodness gracious, what in the world is going on with that? We haven't had any of those lately, and I hope we don't, but who knows, we could. Now, so he's sort of inferring, of course we have warming and cooling. Climate change is normal. And everybody agrees with that. Climate change is normal. Not the type that we're talking about here, and this is where I take exception. Yeah, this is a pattern, that's a pattern. That doesn't seem to be a normal pattern. In this very little time change here, you have had a very, very steep rise in temperature. Incredibly steep rise in temperature. Well, let's look back and see when that is. This is 2000, there's 1800, this would be 1900. That would be basically the 1900s through 2000. What happened then? Early 1900s to 2000. Anyone think of anything? And even starting maybe a little before that, you had the Industrial Revolution. You have automobiles. You have airplanes. You have all these things. We are excavating the earth pulling out fossil fuels. And if you think about, and in the first half of the book, we talked about this some in the other class, those fossil fuels, the oils, the coal, the things that we've been burning in the Industrial Revolution, since the Industrial Revolution, at incredibly rapid rates, those things were formed over thousands, tens of thousands of years to make the oil and the thing. It wasn't anything. So we've been taking radiation that was gathered from the sun for a long period building this. We've been burning them like crazy in the last century or two. So if you were to plot this right next to increases in carbon dioxide in the atmosphere, the lines are very, very similar. He talks a little bit about that later that we'll get to. This is not normal climate change. Nothing else that's gone up that rapidly for that long a time just doesn't happen. Okay? And he seems to ignore it. Okay? Now, data about the ice ages, those are way, way before that, and interglacial warming show that periods of warming and cooling occur in really large cycles. Yeah, way back. During the past 100 years, it's not even fair to talk about this. That last 100 years, from 1900 to 2000, Earth has experienced 2 warming cycles. Well, here was one, and there was one. In between, it went down a little bit for a few years. Now, if I'm not mistaken, one or more of those major volcanic eruptions happened here, which put so much dust and stuff into the atmosphere that it cooled the Earth slightly during that time period. But then, again, look at this. That is one steep curve here. And overall, this is that part of that real steep curve we saw before that just stretched out the horizontal scale. I don't think you can pick 100 years in the history of the Earth before that you would have had that much change in temperature. I don't know. I haven't seen all the data, but I don't think that was the case. And again, he seems to be ignoring that. Okay? Yeah, 2 warming cycles, but things are pretty minor. That's overall a great deal of warming over just 1 century. When you talk about the ice ages, I don't even know how many millennia ago, okay? That's thousands of years, not centuries. Multiple millennia ago, okay? The temperature changes are not uniform. Of course they're not. Now here's what they say here. Temperatures in the southeastern United States have cooled since the early 1970s. I think this was printed before this data was collected, before the droughts we had about 3 or 4 years ago. Those temperatures were incredibly hot. In fact, I think not just in the southeast, but all over the place, we have had record warm temperatures for almost the last 5 or 6 years in a row. Record warms, okay? Hey, record warm's supposed to happen maybe once every 100 years or something like that. To have 5 records in a row, that is unusual, I think. Okay? They say sea ice in Antarctica has increased. And again, I think this is old data. I think it was slightly increasing at some point. Now it's falling off into the ocean like crazy. So I think this is old data here. Because, of course, he was collecting data before he wrote the book, and it took years to get it done. And the slide is from a couple of editions ago, so this is sort of dated. Okay. Now, this is where I get the idea that he's not that much of a believer. Causes of global climate change. It results from a complex interaction of factors. Yes, it does. Everybody agrees with this, I think. Sunspots cause some global climate change. But you know, the sunspot patterns probably haven't changed over the last billion years or so. Okay, so I don't think you can blame everything on sunspots. The Earth's tilt, orbital shape, and axis wobble. Yeah, but that's been it's been tilted. It's been orbital shape. All these things are happening all the time. That can't change an average annual temperature to make a record 4 or 5 years in a row. Those are happening much more slowly than that. The greenhouse gases, water vapor, carbon dioxide, methane, trace gases, yeah, those are also contributing. And if you look at the degree of contributing, especially of the carbon dioxide, possibly the methane as well. Trace gases, it's hard to say what those trace gases are, but yeah, that could be. And then here's another big one that we've been doing. Tropical deforestation. Now, again, the tropics are between the Tropic of Capricorn and the Tropic of Cancer. That's a pretty wide berth. Now, for much of this, especially on the other side of the globe, that's all over water. So not much changing there, probably. But here on our side, this half here, there's a big area of, it covers quite a bit of things. Asia, especially Africa, and quite a bit in South America are in the tropics. Let's start with South America. The biggest country there, much of it tropical, Brazil. Okay? Brazil is heading pretty close to being a first world country. I mean, got a lot of very good things going on there, a lot of progress and other things like this. They don't have a lot of natural resources, though, especially gas and oil reserves. They just don't have it. I don't know why. They haven't found it. Okay? So what they've been trying to do to keep from importing oil, because that's a big outflow of cash to do that, they made a conscious decision to try to grow their own oils. So they have been planting soybeans like crazy, because the soybean has a huge amount of oil in it, and they have a great climate for that, okay, for growing soybeans. So they decided, let's grow our way out of this and not be as dependent on oils, on imported oil. Well, in order to do that, they went to this tropical area here. Huge tropical area. Now, Brazil is this blue country here. See, most of it is in the tropics. Only a little bit is outside the tropics. So a huge amount of Brazil, in fact, a huge amount of South America is Brazil, is in the tropical area. And huge portions of this had some of the densest, thickest rainforest anywhere on the planet. Okay? Those rainforests, hard to overstate. In fact, everything we say may be understating what they contribute to the life of the planet. They have more vegetation, more variety of vegetation, and they have heat, temperature, they have everything they need to support plants to convert carbon dioxide into oxygen, carbon dioxide into oxygen, carbon dioxide into oxygen. We depend on them. The tropical rainforests produce most of the oxygen we breathe. Not the trees around here, tropical rainforests. They keep the whole planet breathing. Well, what did Brazil decide to do? They went in and started clear-cutting huge swaths of tropical rainforest. There were some trees in there I'm sure were very valuable, but they couldn't sell them all as timber and lumber, so they burned them. They cut them and burned them. So here they were taking the trees that pulled carbon dioxide out of the air and put oxygen into the air. they took those trees that had been growing for centuries, maybe some of them and stuff, and burned them, which is using the oxygen from the air to put carbon dioxide into the air. Uh-oh, wrong direction, folks. That was one thing, not the only thing, that's driving up carbon dioxide levels. Other things are the rest of us burning all these fossil fuels and taking carbon dioxide, oxygen out of the air to burn these fossil fuels. Okay. Now that I had heard about for years that Brazil was doing, trying to maintain energy independence. More recently, I've heard about this. This whole country of Indonesia, which is an island nation, okay, it's mostly the purple that you see here. Lots of islands, all within the tropics, much of it right close to the equator. They have tremendous tropical rainforests. Well, there's been another big demand worldwide for palm kernel oil because it's one of the cheapest oils that you can have. It's also really fatty acid type one that's really not one of the better oils for you, like maybe canola oil or corn oil or some of those. None of them are all that great for you, but the palm kernel oil is highly hydrogenated, I think is the term for it. Not a particularly great one for us, but it's cheap. You can produce in the tropics lots of palm kernel oil, and I want you sometime or another. Does anyone have a food product on your desk? You have? Is that something to eat or is that a drink? It's what? Okay, here. Yeah. Oh, gum. Okay. No one has any food product here. Pick any old food. Oh, you got some. Okay. Could you read some of the ingredients for us? What is that? What is that anyway?
Planter's nuts.
It's what?
Planter's nuts.
Planter's nuts. Okay. Well, I doubt if it don't have much. How about the other ones? Yeah. Okay. Read some of the ingredients on that. What's that?
I told the ingredients off.
Oh, you tore the ingredients off? Okay. What I would suggest is go home and pick just about any item off the shelf and look at it. If it has some fats in it, oil has been used in the processing of it, the odds are most of that was probably palm kernel oil. Not one of the better oils for us, but one of the cheapest oils. And what they've done in the Indonesia and other areas too have gone in and again cut down huge swaths of tropical rainforest, more than likely having to burn them because they couldn't sell all that wood. They could have if they tried, but they didn't totally. Again, taking the thing of the driver that pulls carbon dioxide out of the air, put oxygen in, burning it, which then is taking oxygen out of the air and turning it into carbon dioxide, and then growing palm kernel oil. Okay, that's growing plant, but it doesn't produce nearly the amount of oxygen that a tropical rainforest does. Nor does it support the biodiversity, either in Brazil or in there that you would get from the tropical rainforest. We have been shooting ourselves in the foot because of our appetite for oil, our appetite for food products, okay? Cheap food products like palm kernel oil. By the way, any of those would be good paper topics if you wanted to pursue any of those. Okay, let's move on. So global warming. Here's where the guy, I think, shows his colors, okay? Now, they mentioned several things here, and please read it. It's all good stuff. I'm not saying he's not saying the truth, but I think he might be exaggerating some things. I don't know. Global warming. The Intergovernmental Panel on Climate Change, this IPCC, was established by the United Nations in 1988. This was long after people were noticing the changes, noticing the reasons for the change and stuff. So that it was just formed in 1988. Now here's the place that I feel like he's biased. Maybe I'm biased. I know I am. Okay. Despite research, data, and models, the predictions of experts vary. Well, of course they do. Models vary. All sorts of things vary. The vast predominance, though, of experts and everything say, yes, it's happening. No doubt about it. The amount, the degree, the causes, this, that, and the other. Yeah, the predictions are varying, but the vast majority, I would say 90% or better of the scientists say, yes, it's happening. And many of them agree on why. But because there's some experts that vary a little bit in some degree, they make statements like this that make it seem like there's nothing for certain. And I guess nothing is for certain, but the vast predominant think there is. So I think this is a false negative here. Okay. And then down here, this next statement really bugs me. Critical analysis of climate change should be completed before future policies about human-made carbon dioxide are implemented. Wait a minute. Okay, wait a minute. For critical analysis should be completed? I don't think it'll ever be completed. So how much you mean to be completed? Absolutely no variation in the expert's opinion? Never going to happen. If it's an expert, he's going to disagree with some other expert, so he's more of an expert, okay? So this is, to me, almost a ridiculous statement. Because if you did wait till everything sewed up in a nice, tiny little package before you start doing anything about future policies, in my mind, it's going to be way too late. Because before you complete all this, we're already going to be in what in the Navy we call extremists. In other words, past the point that you can't get out of the problem. So I really find this statement to be bothersome. Okay? Now, maybe he didn't mean it that way, but that's sure how it sounds to me, especially when you say this. Despite research, data, and models, the predictions of experts vary. The predictions of the weather varies, okay? You can go to the one station will say, well, now this model says this and this model says that. It's probably going to be somewhere in between, okay? Yeah, predictions vary. That's why they're predictions. You can't say exactly what's going to happen. So that, to me, is a false negative statement. Yeah, they do vary, but it's trying to imply that there's no consensus. And there is a complete consensus, but the vast majority say, yeah, we're rapidly running out of time to do anything. So then this next statement becomes ludicrous. Okay, we can't wait until we got everything tied up in a knot before we do anything about future policies, because by then it's going to be too late. I'm convinced it will be way too late. Okay, sorry, that's my soapbox. I'll get off of it. Okay. Now, in your text on page 597, there is a case study on El Nino. Now, most of you, have you heard of El Nino before or not? Okay, read this. It is a fascinating, it's not, I've read better descriptions of it, but it's still good. Okay? El Nino, somewhere off the coast of Peru, I believe it is, there's a spot in the Pacific Ocean that for some reason sometimes gets quite warm. And when it does, that's going to produce changes in climate or weather for huge portions of the globe. And that process is called El Nino. And the reason they call it El Nino, that is the, I think, Spanish word for the Christ child. And it comes around Christmas. That's when they detect the big temperature change. Everything else that's getting cooler, that spot out there in the Pacific is either still as warm or getting warmer or something. Something weird's going on, and it's usually around Christmas time, so they call it El Nino. Okay? Now, it happens about once every 7 years or so, 3 to 7 years. Not always the same period, so it's hard to predict. and it will be at different degrees. So read this. Now, in between El Niños, there's usually a La Niña, which is the feminine of El Niño, which is going in the opposite way. I think the waters and stuff are a little bit cooler than normal, and that has a less dramatic effect, but still has an effect on climate everywhere, especially here in the U.S. And El Niño is really going to create. I bet you, I don't know if this for sure, we can ask Jerry Tracy if we get to go next week or the following week to the Weather Center, if they think this, which to me is very unusual weather pattern, very wet weather pattern, if this is somehow connected to El Nino. I wouldn't be at all surprised if it wasn't. Maybe not to a huge extent, but I bet you to some. Please read this, because I bet you he will mention El Nino. If you've read this, it'll make more sense what he says. There was also someone mentioned here, Wilhelm Thurman Gorin Brzezinski, or something like that. Okay, I don't know how to pronounce his name. He was a Norwegian scientist. No wonder it's so hard to pronounce. Brzezinski, I guess is how you say his last name. He was very talented family. Father was professor of mathematics at California, Christiania, now Oslo University. Highly influential geophysicist who clearly shaped his son's studies. He held chairs in Stockholm and Leipzig before founding blah, blah, blah. So I'll let you read that if you want to write on him. This can't be your source. This can give you ideas. Go to somewhere else to get your source. Now, remember I said, I'm going to do this. I'm going to go back. I don't know why he didn't put this in. All right. Remember I said, look at this steep increase in temperatures here. That's not normal. That is way too big a change on a very short period of time. And that was somewhere between early 1900s or so. Somewhere in the 1900s. Here is a graph showing carbon dioxide concentrations from 1870, which would be somewhere right in here, until the year 2010. Look at that curve. Look how close they are, closely related they are. Just an incredible rise in carbon dioxide values, amazing increase in temperature. Don't tell me they're not connected. They seems like they've got to be, okay? And what's more, so many, vast majority agree that it's a problem. It's not that it's just one person saying, hey, we may have a problem. Or even a minority. It's the vast majority saying, look, it's here. We got to do something about it. Okay? All right. You hear me say this every chapter. Nothing replaces reading the chapters. Nothing. Okay? Please read them. Try to read them before I go over them. Maybe read them again afterwards. I think you'll find it make a lot more sense that way. Even maybe what I'm saying will make more sense. There is, at the end of a chapter, a summary, which has a lot of italicized terms, which are pretty important ones. It's a condensed version, sort of like Reader's Digest, condensed version. Do people even have that anymore? Then there's key terms. Now, the summary is probably a little shorter than most summaries, and the key terms, that list may be a little shorter than most lists. But then there's applying the concepts, and there are 45 questions, maybe a few fewer than normal there, too. Questions for thought, 14. That seems to be a little bit on the short side. Further analysis, 4. Maybe that's a little bit, too. So anyway, well worth. Those are things. I think that applying the concepts is the best study guide, but the other questions are good, too. The parallel exercises are more like the examples in the text which largely call on previous chapters to do them, but you might find some of those worth looking at as well. Okay. Finish chapter 23. Any questions on 23? Okay, let's look ahead for next week. We think, and as far as I know, we'll be going to the planetarium we'll leave here at 1:15. We got to in order to get there by 2 o'clock. If you're coming from elsewhere, leave in time to get there by 2 o'clock. Stanford University, 2 o'clock. Does anyone need transportation? Some people are here that weren't here at the first of class. Okay. And I can take up to 3 in addition to me in my car. Okay, vehicle. It's a small SUV. Okay. I could do 4 if 3 in the back seat. If I think it'd be okay. All right. Now, the rest of you, when you can, carpool. There's a decided tight parking situation at Sanford. You may not all be able to find parking places in the parking deck, so as much as you can, pool together. Okay? If we needed to, I would gladly get the school van, but y'all don't sound like you're interested in going in the school van, so I'll just take my vehicle then. Now, that will be, we'll leave here at 1:15, be there at 2 o'clock, and you'll start to show someone shortly after 2. My guess he'll go for at least an hour, probably closer to an hour and a half. I doubt if he'll go as much as 2 hours, but he might. So anyway, let's just say from 1 to 2, 2:30, something like that. We got plenty of time to make it back to campus here. So let's say we leave it at 3. Okay. Starts at 2, goes till 3:30. We're back here by 4:15, right? Easily, by 4:15. All right. We still have class to go, so I'll start 24 today. We'll continue in 24 on Tuesday. The last 30 minutes on Tuesday, we'll have the test on 23, like normal. Last 30 minutes, we'll have the test on 23. That means from 5:15 till 5:45, the test on 23. So please, folks, try to come on back. If you don't, you're going to have to make up the test during my office hours. I don't have many office hours, so please try to get it done, preferably Tuesday. Okay? So we'll start 24 today. We'll continue 24 for the little bit of time we have on Tuesday, and then hopefully finish 24 by Thursday. Now, Thursday may be the field trip to Channel 13 weather. I'm going to try to arrange that. If we do, we'll leave here at 1:15. We'll get there by 2 o'clock. It'll be almost just like the planetarium. I doubt if he'll go much over an hour with us there. He might, but usually it's about an hour. Then we'll come back here. We'll have time to finish up 24, I'm pretty sure. If not, we still have the following Tuesday. On the following Tuesday, we will finish 24 if we haven't already by next week, and then we'll have the lab for 24. The lab for 24 is an in-class lab. I've made up the lab. You'll use your books. You can use my book. You can use any books, and you can look up the information. Okay? It's a paper lab. There's nothing we're going to be doing per se. You'll be doing it among yourselves. Okay? And work together as lab, because it is a lab. And then either Tuesday or Thursday of then the following week, we'll have the test on 24 as well. Okay? And then the Thursday of finals week, that's when our final exam is. And that final exam is probably going to be the shortest and easiest test we've had all term. It's going to be matching, not multiple choice. So now both of the next 2 tests have some multiple choice and maybe some fill in the blanks. Okay? I think they both do. But the final exam is matching, which is pretty easy, pretty short. So whatever day we have that, I think it's that last Thursday, why don't we plan to have pizza that day? It seems like it's a lunch hour anyway, isn't it? So let's have pizza first, and then we'll have the final exam, and you'll be out of here in plenty of time. Okay? What you think of that? All right.
You said Thursday?
That's Thursday of the following week,
Oh.
at the end of the term, mini-term.
Oh.
See, we have class next week, which is maybe 2 field trips and some class in between. And then the next week is our last week, when we'll have the last day of class on Tuesday and the final on Thursday. I'm pretty sure that's how the schedule is, isn't it?
The final on the 7th?
What's that?
The final will be on the 7th?
Okay, let me see. Next week will be the 26th and 28th, yeah, and then the following will be on the 5th and 7th. Yeah, final on the 7th. Isn't that what's on the calendar?
Well, I just thought that it ended on the 5th.
What's that?
I thought the entire class ended on the 5th.
Okay, that's the last day of class. But isn't the final exam then on the 7th?
Okay, I get you.
I think that's how it reads. Does anyone have that in front of them? I could pull it up, but it would take a while to get it to come up. But I believe that's how it is. I'm not sure. Does anyone know? Okay. No one can pull up real quickly the college calendar.
Students meet?
What's that?
It's on the students meet?
It should be. On the Lawson State webpage, at the top, there's a bunch of blue tabs at the top, and one of them says academic calendar. You see that? On the Lawson State webpage. Did anyone get it quickly? Anybody?
Is it academic calendar?
Academic calendar, I think. It says something about calendar. I believe it's academic calendar. Okay, you see the top up there where it says student suite, employee suite, and stuff like this? Right down from that, like 2 or 3 other over, is academic calendar. You see it? Did you pull it up? Open it? And go to the month of March. It probably takes a while on the phone.
It says it's the 5th.
It's what?
It's the 5th.
Is the last day of finals?
The final exam.
Final exam is on the 5th. Okay, well, you're right. So that means we have to have everything finished next week, because the final is on the Tuesday of the following week. So I think we could do it, even if with 2 field trips. Now, maybe we'll have the last test on that Tuesday and the final exam on the Tuesday, but we can handle that. We could even have the lab and the last test and the final on that Tuesday. I think that's probably what we'll wind up, because none of those take long. The lab you can probably do easily less than 2 hours. The last test, less than 30 minutes, and the final exam, probably less than 15 minutes. So still, it won't be a full day. So we'll do that on the Tuesday then. So can we have pizza that day, you think? Okay, let's plan for that. All right. I hit the wrong key. Sorry about that. Okay. Let's start chapter 24. We have what? About an hour, right? So let's get started on chapter 24. All right. Chapter 24 is Earth's waters. Okay? And guess what? Just about every chapter we've had, at least since we started the geology part, has had the concept of cycles. Okay? The concept here is full of it. The hydrologic cycle is water evaporating from the ocean. We did this at the beginning of chapter 23 also. Transport by air, masses, precipitation on land, and then movement of water back to the ocean. We had it at the beginning of chapter 3. Here it is again. That's the core concept of this chapter. We're going to be studying the Earth's waters, okay? And they show a nice little glass of water here. Now, there's a really nice illustration. I can't remember where I've seen it. I wish I could find it. It shows a huge tank of water that represents the Earth's oceans. Well, we'll see it in a slide. I'll hold off of that for a minute. Yes?
Where are we going to meet at Tuesday?
Say again?
Where are we going to meet at on Tuesday?
In the classroom here at 1:15.
Okay.
At 1:15. We're leaving the classroom here at 1:15. We'll talk about where to meet. If cars are going to follow me, we'll talk about that at 1:15, where to do. But I'll be driving out of the building at this light out here, heading toward the hospital, the light at the hospital. If y'all can come around and get behind me, and we'll leave from there, okay? And I'll talk about the route I'll take. I don't go all the way down the Western Superhighway and hit 150 there. There's too many lights. I turn at a CVS before that and go around the back way and miss most of those lights. But if y'all are behind me, you'll see where I'm going, okay? And if y'all have phones, if Patel is in the car with me at least, or anyone else in the car, y'all can keep in touch in case someone gets lost or loses sight. You say, hey, could y'all pull over because we can't see you anymore. We can do that. So if y'all work that out before class next time, okay? All right, water on the earth. First topic. 24.1. The most abundant chemical compound near the Earth's surface is water, okay? Look at the globe. Most of what you see is water, and that water goes way deep, too. In places more than a mile, way more than a mile, maybe several miles. It covers 70% of the surface of the Earth. Land only covers 30%. That's a lot of water, and it's deep, okay? 97% of that water is in those oceans, okay? That's salt water, briny water, okay? Only 3% of that water is fresh water, water that we could drink, because most of that is ocean water, salt water, okay? Now, of the 3% that's fresh water, which doesn't sound like a lot, but it's still a lot of water, 2/3 of that are in the ice caps, the polar ice caps and glaciers and things like that. 2/3 of that fresh water is in the ice caps. But guess what? It's getting less every year. I'm not sure it's even 2/3 anymore, because those things have been melting like crazy. And guess where they go most of the time when they melt? Into the ocean. So there goes our fresh water back into the ocean again. So less than 1/3 of that water, of that 3%, so less than 1% of the water on the earth is available as drinking water. And not all of that is really all that available. So let's go back to the hydrologic cycle, which is a cycle of water. Again, saying the same things our chapter 23 said. There was a couple figures there. Same thing that our core concept said. First, water is evaporated from the ocean, especially in those areas that have high solar radiation. Lots of that is ocean water. It's evaporated from the ocean. The water vapor is transported to other locations, some of it over land. Precipitation returns the water either directly to the ocean or indirectly. So guess what? Most of this water that's evaporated in the Pacific, look how big the Pacific is, that's evaporated from the ocean, it's going to rain right back into the ocean. It's not even going to make it to dry land, okay? So it's going to, it's transported to other locations, and only a little bit of it is precipitated back. The precipitation returns water either directly to the ocean or indirectly over land, and then ultimately it goes back to the ocean. Okay, I think this slide will stay up here. Now, here is an illustration of that. It's even worse than it sounds here. Okay? Of all the water in the earth, on the earth, around the earth, through the earth, okay, This represents it all, and they say actually more than 97%, 97.6% is ocean water, which is salty, non-usable for crops, non-usable for drinking, non-usable for anything except evaporating to try to get its rainfall. So only 2.4%, they are pretty generous here in saying 3% is fresh water. Only 3% of that water is fresh water. And they say here 2/3 an ice cap. They say more than 3/4 is an ice cap. I have a feeling this is an older slide because I bet you between that one and this one, you had already lost some of that from the ice cap. Okay? And then, this is hard to believe, of what's left, the sediments underground make up a little more than 1/5 of the fresh water. That's what we call groundwater, okay? Now, all the water that's in the rivers, the streams, the lakes, the creeks, the swamps, the everything else, bodies of water like that, that is less than 1%, 0.8%, okay? And then the water in the atmosphere is way less than that, 0.004%. So that's negligible. That's in the atmosphere. It's important, very important, but not that much. So all of our rivers, the mighty Mississippi, and all the rivers in the world, less than 0.1%. Lakes and everything else, the Great Lakes, things like that. Okay? This is the fresh water, that little bit there, most of it's salty. Now, here's the hydrologic cycle. We saw this in the previous chapter. Here it is, the water evaporating off the ocean, going up into clouds. Some of this falls back into the ocean. Here they give percentages. Precipitation back into the ocean. 77% of that water that evaporated rains again into the ocean. Just waters the ocean again. That hits the land is only 23%. Thank goodness we get it though. Okay? And that hits the land, it's hard to follow these percentages. This 84% that evaporates off the ocean, where's the other 16%? Well, that's evaporating off the land. So these two go together, these two go together. Okay. Now, runoff from the land, the 7%, I don't even know where that comes into play. Okay? It isn't part of any of the other percentages here. But that's saying of that falls onto the land, 7% of that runs off. Directly runs off, doesn't get used for anything else. Okay? So this one's a little bizarre in there. 100% is based on the global average of 85 centimeters per year precipitation. Goodness gracious, I think we've had 85 centimeters of rain since January. Maybe more. Okay, I don't know. I may be wrong on that. I'm not used to thinking in centimeters. Okay, precipitation. Freshwater. Precipitation is the basic freshwater source. We really don't get freshwater any other way than evaporation off the ocean and precipitating on the land. Now, 2/3 of this goes right back into the atmosphere. We don't get to use it. The remaining 1/3 of that falls as precipitation runs the runoff flowing downhill, or it gets absorbed into our groundwater. Now remember, the groundwater contains a lot of our water. Look at this. This is sediments underground. That's a good portion of it there. That's valuable stuff there. Okay? Now, sorry. Okay? So runoff flowing downhill, I guess that may have been the 7%. Groundwater absorbed into the surface that can emerge elsewhere as runoff because it may get absorbed up there on Red Mountain somewhere, but then come out as a stream somewhere below Red Mountain, or something like that, okay? It could come off as runoff still. The runoff groundwater distribution depends on several things. One is your soil type, okay? If you've got a sandy soil, you're going to have more of it goes into groundwater. If you have a clayey soil, little of it, less of it, a lot less, goes into groundwater because it's hard for the water to penetrate a clay. If you have paved the parking lots, none of it runs into the soil to get into groundwater. It all goes as runoff, okay? So that's soil type. That's really not a soil type, so I threw that in. Dryness depends on the soil type and dryness. I don't know why they put it in here, but it is important, but it's pretty minor importance. Actually, a dry soil will absorb less water than a wet soil. That sounds bizarre, but it's true. Because if a soil is very, very dry and you put water on it, most of it's going to run off. If a soil is already damp, then the soil particles already have coatings of water. It's much easier for the water to move through those pores than ones that's totally dry. So that's why they say it depends on soil type and dryness. The amount and type of vegetation, that is crucially important. The more vegetation you have, the more you delay the runoff. The less vegetation, the more runoff you get. So more has potential to get to groundwater if you have the right kind of vegetation, the right amount and the right type. Now, what do we mean by right type? Grasses are better than trees, okay, for getting water into the groundwater and keeping it from running off. The steepness of slopes, oh yeah, that's really important. A really gentle slope to flat surface, more of that water is going to go into groundwater. The steeper the slope, the water is going to go downhill so fast, very little has a chance of getting into groundwater. Okay? And then the rate of rainfall. Frankly, these kinds of rains we've had the last few days, except for a couple of really intense showers, have been the best type of rain ever in my mind. It's slow, drizzly, soaking rains. They're miserable to be out in, but they're the best for getting water into your groundwater. Make sense? I'll leave that a little bit. Oh, yeah, I think another slide's coming up here. All right, here's sort of an example of this. Here's a stream. The bad news here, I see no vegetation anywhere here. So let's imagine there's vegetation there, okay? Or maybe not. Then most of this is going to run off into the stream, run off into the, ultimately into the ocean. First to a river, then to a bay, or whatever. Okay, however, if a lot of this does make its way through the soil, then it gets into a semi-wet area here, but down here you have huge supplies. Now, not always easy to get to, but this would be where most of the pores are soil pores are filled with water. Up here, only fractions of them are filled with water, but this is the transport. At some point down here, you reach what they call the water table, and that now this stream actually intersects with the water table somewhere here, and then it's feeding the groundwater, or groundwater is going into the stream. It's hard to say which way it's going. Okay. So this shows that some of the groundwater goes into runoff, some of the runoff may make its way to groundwater. But the best is that it absorbs directly into the soil. You can improve that by vegetation. Now, are any of you big gardeners? Not at all. Okay? Oh, you are good. More plants or vegetables? I mean, flowering plants, vegetables, or what?
Vegetables.
Second? Vegetables, wonderful. Do you have exposed soil around your vegetable, or do you mulch?
No, use fertilizer.
Yeah, fertilizers, that's for sure. But do you mulch? Do you put, say, pine bark, pine straw?
Oh.
No, okay. Yeah, open. Okay. So the soil is exposed. Another thing that they didn't mention here, and if you have a big, large-scale garden, you can't do it. We have a really small garden, so I try to get stuff around it to keep the water from evaporating. If you can't have vegetation, which you don't want vegetation in your garden, you don't want grasses growing, you want those plants. But if you can put things around them like pine bark mulch, now I wouldn't use something like sawdust, that's not particularly good, but pine straw or something like that that covers the soil like vegetation, that keeps the moisture in better. So that's called mulch. So for a small garden, and we don't have much of one because we have too much shade, but we do raise, we have a few pepper plants and we have raised herbs. My wife likes to cook with herbs. But I try to cover the soil with whatever I've got, leaf mulch, anything like that. That keeps the rain we're getting now. Who cares? Okay, but once that summertime comes, if you can keep a good mulch there, you can keep a lot of your water in. Yeah. Okay. So let's move to surface water. We started with the rain water. Let's move to surface water now. Okay. This is collectively the water in all your streams, all your ponds, all your lakes, your reservoirs, okay? Everything, the fresh water that's on the surface, not in the ground, on the surface. Okay? Now this is going to introduce a concept called a watershed. That's not a shed where you store water. This is places where the water lands and then collects. Okay? Surface water. The land area drained by a stream or streams. Okay? I was driving from here to Birmingham East Campus yesterday, just after one of the rains. And boy, I crossed several streams that were just flowing like crazy. Well, all the land area around those streams that the water went from the land to the stream, that was the watershed for that stream. Okay? That's what we mean by a watershed. The land area drained by a stream or a number of streams. Two adjacent watersheds, like I said, I've crossed over 2 or 3 of these streams, and between any 2 of the streams, there had to be a high point that was called the divide. The water on this side went to this stream, the water on that side went to that stream. That's called a divide. Now, every continent has at least one, and usually more than one, divides. We have 2 major ones. They are called continental divides. They separate the big watersheds draining into opposite sides of the continent. Okay? Now, we're not a whole continent. We go from the Atlantic to the Pacific, so we're this portion of the continent. Well, here we have the Appalachian Mountains approximately. They form a continental divide. Some ridge in the middle of the Appalachians. Now, this goes well below the Appalachians, but some place there divides the water that's going into the Atlantic from that that's going into the Gulf. Okay? And also that which is going into the Pacific. Well, the Appalachians don't do much there, okay? But they are a divide here. All the rivers on this side, now these are going into the Gulf. This is just showing Mississippi. But over here in Georgia, there's the Savannah River there, the Oconee River, the Oconee River, Oconee's up here, Oconee down there. All these rivers flow into the Atlantic, in here, and here. And in Florida itself, there's a divide. Rivers on this side go into the Atlantic, on this side go into the Gulf. Every separation between 2 rivers or streams is a divide, sending them in other directions. The biggest watershed in the continental U.S. is the Mississippi River watershed. Now, it's more than just the Mississippi, but all of it goes through the Mississippi. Okay, the Missouri goes up here. This is the This is basically the Mississippi here. In St. Louis, the Missouri comes in and goes up through here and wanders around, and things feed into the Missouri here. This is the Rocky Mountain Continental Divide, okay? Everything on this side flows into the Gulf. Everything on this side flows into the Pacific, okay? But even here, there's another divide between the Columbia River watershed and the Colorado River watershed. This is what Grand Canyon is on in here, and Lake Mead is right, and there's big major. This watershed feeds most of the West Coast. They draw water from this. This is another watershed, or a number of them. But these are the three biggest ones: Columbia River watershed, Colorado River watershed, and the biggest is the Mississippi. The Ohio River goes through here, Mississippi here, the Tennessee River goes through it there. There's just all sorts of rivers, as I said, Missouri River here. All kinds of rivers feed into the Mississippi, and it feeds into the Gulf of Mexico. Now, other, like the Chattahoochee is here, it flows, here, it flows in here. Apalachicola goes here. There's all sorts of rivers that flow here too. The Mississippi is our biggest watershed, followed by the Colorado and Columbia, also pretty big watersheds. Okay, almost the whole state of Idaho is this one. This, I think, is the Snake River that goes here. This is the Columbia River here, makes the boundary between Washington and Oregon. So that's that. Okay. Rio Grande goes down here, so it has its own watershed, but it's much smaller than these three rivers. Okay. So, a continental divide separates the watersheds draining to the opposite sides of a continent. The continental divide here goes into the Mississippi, into the Gulf of Mexico. The continental, on this side of the continental divide, goes into the Pacific. This part, a lot of this part, there's another continental divide here, a smaller one, into the Atlantic and this into the Gulf. Okay, this all shows. Okay, now, when we were up in Yellowstone, I thought it was going to drive my wife crazy, but she got interested in it too. When we were driving through Yellowstone National Park, I'm pretty sure, and that's right up here in this part of Wyoming, part of it into Montana and stuff like this. Okay, we kept crossing it. It's not a smooth straight line like this. It's really wiggly. We must have crossed the Continental Divide 4 or 5 times just driving through Yellowstone. And it was so interesting to, as we crossed the Continental Divide, the next stream I saw, I'd say, okay, which way is this going? Oh, that one's going north. Is that going to the Gulf or is that going to the Pacific? Because every time we crossed the Continental Divide, the next water we see would be going in the opposite direction. On one side, it was going to the Pacific, the other side going to the Gulf of Mexico. And you couldn't always tell because some of these things went north and south in all sorts of ways, and it was really fascinating. And Karen just got really amazed by it. Yeah, these are going to opposite parts of the continent, just crossing over a few miles drive there. Okay. So let's now go to groundwater. That was surface water. This is groundwater. This is underground water that has made its way through the soil profile into open spaces between the rock and soil particles. I call those the pore spaces, P-O-R-E spaces, and it saturates those pore spaces, usually pretty far underground, and that water saturates that. That's what's called groundwater. It percolates downward from the surface. That's a slow movement downward. 25 times larger supply than the surface freshwater. All the lakes, all the rivers, all the Mississippi, the Missouri, all those rivers, all the streams, all the swamps, all the everything, 25 times larger supply is in groundwater than is in all those put together. Now, often this is within 100 meters of the surface. And what is there is called the water table. We haven't gotten to that slide yet, but we will. Okay, so this groundwater is often within 100 meters of the surface. Well, what's 100 meters? That's a football field stood on its end, going down, and that would include one end zone that would be at 100 meters. Most of that groundwater is within that top 100 meters, which is pretty deep when you think of it. When we drilled the first well on our farm in Georgia, I'm pretty sure my dad said it was about a little over 100 feet deep before they hit fresh water. Okay? And we used that well for many, many years. It was mostly to water cattle and stuff like that, but that was long before we moved to the farm. When we did move to the farm, we had to drill a well for the house, because that one was over near the shed, another part of the farm. So we had to drill a well there, and that one we went at least 125 feet. Now part of that because it was up on a hill, but the other part is the water table was sinking. Okay. Well, when my grandmother and great aunt moved to Georgia, and lived across the road, they drilled the well. It seems like it was around 125, maybe 150 feet too, before they got good water. Since then, the one at the shed dried up. It was great water, but it dried up, so they had to drill a second one even deeper because the water table was receding, going deeper. And then when my wife and I built the house that we built, they first hit water about 125 feet, but it wasn't sustainable. It wouldn't keep flowing. So we had to go deeper. So we went at least 150 to 200 feet before we hit good sustainable water. Now, why was that? Well, we had had droughty type years for like 8 of the past 10 years. That contributed some. But because they had droughty type conditions, farmers near us, not real close, but near us, decided to irrigate so they could make better profits. Well, make more crop, I'll put it that way. I don't know how much the profit they made. And that, I think, was dropping the water table. Now, fortunately, this last year has been a very wet year. Hopefully that water table has come back to some extent. But it is a very variable quantity. So, how does this groundwater flow? I'm sorry, I haven't been turning the pages of the book. There is a very good blurb on page 609. I should have mentioned it earlier. It's on water quality, which is really becoming a very big issue. Okay? I'm going to take some cities in Florida, for example. I'm going to probably use Tampa, probably Miami, some of those other big cities. Okay, Florida, by the way, has the richest supply of water of any state in the Union. They get more rainfall. I don't know about Hawaii, probably, but more rainfall. They have more groundwater. They have all these things, but they also have huge population explosions. You know, the snowbirds that used to go to Florida in the wintertime, a lot of them stayed in Florida, okay? Florida is really overpopulated now for its natural resources. So more and more cities are pumping more and more water to feed their cities, you know, to provide fresh water for everybody. So what's happening? Salt water is encroaching the groundwater. And some cities can't use their water anymore. They have to either drill deeper or go further inland and pipe it out. They have to do something because of that. Now, they've also had a few years of drier than normal conditions, but they are really messing up Mother Nature, okay? Plenty of water was there. It's not as plentiful. So that's where water quality comes into play. Even though we have the water, some of it is polluted. Some of it by salt water, like I just was describing. Others might be because of chemical spills or things such as that. Let me use Anniston, Alabama as an example, just east of here. There was a big plant, back in its day it was called Monsanto, really big chemical company, had a major plant there. They made a lot of the transformers that all electrical utility companies use to drop down the voltage. They used in those transformers a chemical named PCBs, I think it is, polychlorinated biphenyls, okay, which were toxic. But they didn't realize they were all that bad. And when they finished their producing these things, they'd rinse out their stuff and let the water go into the streams near the plant and into the groundwater near the plant. And unfortunately, those were areas that were inhabited mostly by the poor, and unfortunately mostly by poor blacks as well. Well, what happened? They started getting high levels of cancer from those neighborhoods. And then they realized those PCBs that Monsanto had been dumping into the water system, runoff water, that contained carcinogens, things that cause cancer. People were using, the kids were playing in the water, okay? People were using the water to irrigate their gardens and eating the vegetables from that, or else the banks would overflow with a big rain and the gardens would get inundated by it. Large number of cancers. There were major lawsuits. I don't know the final verdict, but I think, and by the way, Monsanto sold the company years ago, and then the different companies that have owned it all claimed it was somebody else's fault. So it's been a political football. My guess is that people who suffered from it mostly died. They didn't get any compensation. Not good. Water quality, big issue. Okay? Probably too much there. Okay? The picture of the watersheds is on the next page. Surface water we just talked about. Groundwater we talked about. That's on page 611. 612. I think this is where they talk about groundwater flow. Okay. I think I've already mentioned some of this, but that's about where we are now. Are we doing on time? Okay. Now, if that soil, remember we said the soil type, if the soil is a sandy, gravelly soil, okay, what you have is a lot of open pore spaces. Now, I want to expand on that a little bit. What you have is a lot of large pore spaces, okay, large pore spaces. And this is very permeable to water flow, okay? It's a lot like, have you ever gone to McDonald's or some equivalent place like that and gotten a milkshake with one of those great big old round straws, right? And you can just barely suck the milkshake through that, okay? But you can. Use that in a Coke or something like that. Boy, really easy, right? But you've also probably gone there early in the morning and bought you a coffee, and their coffee is notoriously hot, right? So you probably got one of those little stirrers that has a tiny little hole in it, and you can sip the coffee also slowly to keep from burning your mouth. Just imagine trying to take that little bitty coffee stirrer and drink your milkshake through it. You can't do it. You're going to pop your eardrums trying to suck the milkshake through that little thing. The point is, the larger the pore size, the easier it is for water to flow. Same type thing. Very permeable to water flow. Whereas a clay, this is where I disagree with it. they say low porosity. Not necessarily so. A clay can have a pretty porous system, but the thing is, it's very small pores. It's just like those tiny little coffee suckers, that you try to sift through. They're so small, it's hard to get anything through them. That's why. It's not so much low porosity. It can be low porosity, but it's more so small pore sizes. Why? Because the clay particles are so small. So you may have a lot of pores between them, but they're also tiny that it's hard to get water to move through them. Now, the other thing about clays, they tend to flatten and go this way. So what you have to have is water goes this way and that way and this way and that way. It can't go straight down. Okay? That's the other thing. It's impermeable when saturated or compressed. Now, this is true. Clays are real easy to compress because they have those flat particles. So you run over them with your cars and stuff like that. You press them down. You completely destroy the porosity. You limit it to very, very small. That will create low porosity. When you compress the pore spaces, then you have it. But when it's saturated, again, it's real hard for the water to move because they're such small pores. Such small pores. So impermeable is a good word, but it's not because of low porosity, always. It could be, but it's quite often because of small particle size, pore sizes. And that's because of small particle size too. Okay? And here's the example of that. Here is the sandy or gravelly particle. Notice how large the pore sizes are. So it's easy for water to go through. Very easy. Now, the clay particles, they have drawn them well that they drill sort of flat-like, but they show no water going through it. There's actually lots of pore space here, not as much as they drew there, but lots of pore space, but it's so tortuous to get through, it takes water a long time to do it, making it impermeable. Especially if you compress these, look like these have been, then you have even more difficulty. But if you were to add up, literally, all the pore space here, the porosity here isn't far from being here. They've really made this too big, but you still have lots of pore space, but they're all very small. That's the problem with clays. Water moves through it very, very slowly. Now, if you also compact the clays, compress the clays, then almost none can get through. That's why, have any of you ever traveled on a dirt road or a driveway or something, and you get the mud puddles in there? You pack down the clay there and water can't go. They'll hold water for days. Even when it's real dry outside, they'll hold it for days because the water can't penetrate where you've run over with your car tires.
That's how my road is right now.
Yeah. Oh, I bet you. A dirt road now would be miserable to travel on.
Mine's gravel.
Gravel, yeah.
But it's still the same issue.
Yeah, and that's because under the gravel, the clay particles have been pressed together. It will not let the water seep through, or it's very, very, very slowly. Okay. So, what do we have as far as groundwater deposits? Okay. Again, this is about that same page. What we have are zones of saturation. Okay. Remember, you have the soil up above that's usually got air space too in the pores as well as water. And it flows through that, but somewhere it collects into the groundwater where it becomes saturated. So that's the zone of saturation. It's collected groundwater above some impermeable layer. It could be a rock, it could be a very densely clay type area or something like that just doesn't allow it through. So where the surface, the top of that boundary, that's the zone of saturation, and above that is unsaturated, that's called your water table. I've already referred to that several times. That's the top of that zone of saturation. Water can move laterally within the zone of saturation, but it can't move very far down because there's an impermeable layer holding it up. But it can move laterally. Now, this is a really good term, an aquifer. Okay? It's a subsurface layer of highly permeable material capable, I do not like that term. It's not to produce water, it holds water, okay? So it doesn't produce it. It'll produce it if you drill into it and pump it out. But what it is, it's a highly permeable layer that you can easily pump water through, an aquifer. Now, sometimes you think of it as an underground river. That's a bit extreme because you always have material there, solid material, but very highly permeable material that the water is in the pore space. Now, if these are deep enough aquifers, that's called an artesian aquifer. The well at our farm that we had to go so deep to get, we got into artesian water. At least it seems like it is. It is such good water. I mean, it's just great. No sandiness to it and stuff. Nice artesian aquifer. And now, typically, these are confined under pressure from water at some higher elevation. Okay? Now, here's a picture that sort of describes it. Not too much for the artesian part. We'll get that one on the next one. But this is what we're talking about here. Here is your soil that is permeable. It allows water to go through, but it's not saturated. This is good for growing plants because a healthy soil, would you say a healthy soil is solid, liquid, or gas? Solid, you would say. Well, the soil particles are solid, but guess what? To be a healthy soil, it's all three. Okay? In fact, this is the breakdown they usually do. They say about half of the volume should be solid soil particles, and the other half pore spaces. So when they showed this illustration back here, I'll be right back. When they showed this illustration here, that's about halfway particles and halfway pore spaces. This one's a bit more particle than pore spaces. To be a good and healthy soil, it needs to be about 50-50. Okay? Now, oops, too far. Yeah, I think this is where I belong. Yeah. Okay. Now, of the pore sizes, pore space in that healthy soil, you want half of it to be air and half with water. Not that way, all mixed together. Why is that? Because the roots need air and they need water. If it was saturated, your roots can't live. They can't breathe. Roots breathe just like we do. They respire. They need oxygen to burn energy to give off carbon dioxide. So roots need to breathe. If you ever overwater your plants and they start getting sickly looking, that's because you have overwatered them. There's not enough the pore spaces are saturated with water. Plants can't live there. So this is where plants do well. They have air in the pore spaces. They also have water in the pore spaces. Water tends to move down into the saturated permeable layer. Somewhere down here, you have an impermeable layer that keeps the water from going in deeper. That could be groundwater, goodness gracious. What is that called? Bedrock. Okay, bedrock. That's not where the first one lives somewhere. Okay, bedrock. That's actually rock that can't go through, or some other layer. Okay, so here is your water table here. So the water table is the top of it. Okay. Now, if there's some place that the soil drops, there's a dip here, then this is going to fill up with the saturated groundwater. Okay? And that's going to be a lake right there. You may not even see anything feeding in or feeding out because it's living on the groundwater, the saturated groundwater. The water table here takes the bed downward. That's just because of sloping downhill. Here you have good soil that you can grow plants on. It's better to have plants. And you may even have a spring coming out here with another dip here, which could be a river flow, or a swamp over here. Okay? These are all real close to the water table. In fact, most swamps are where the water table does reach the surface, especially if it stays swampy close to here. Ultimately, even this groundwater will make its way to the ocean. Hopefully not ocean water is making its way back this way, but groundwater is making its way to the ocean. So that's the shows your zone of saturation. The top of that is called the water table. Not just there, but here and here and here. You know, that's all the water table. Your impermeable layer that holds it up. And that's where huge amounts of our fresh water is in the saturated groundwater areas. Now let's turn to a slide that shows the aquifers. All right. Now, I don't really care for this one that much because usually an aquifer doesn't expose to the top surface out here. This really doesn't make sense. It would be on down here, but it's a very, very, very deep aquifer. Okay? So deep. Let me give you this illustration. Back during Vietnam, that was in the time I was in junior high and high school, basically. Early years in the war, we weren't really doing that well because we had not been used to jungle fighting, what did they call it, reconnaissance fighting, guerrilla warfare. We hadn't been used to that. We weren't trained for that. And we weren't used to not having nice bases to fly into and deliver supplies and having good systems. They didn't have it in Vietnam. It was a pretty primitive in some ways type area. And soldiers were having to go over there and set up bases out in the middle of nowhere. And we weren't doing too well at that. Okay, good deal. Thank you. Now, our neighbor right across one of the roads from us had a big cattle operation, had big open fields, but he had sort of cut down his cattle. I don't think it was making a lot of money anymore. So he had cut down his thing. Well, the government came in. Fort Gordon is real close to where we live. They needed to train their troops to live out in the boonies without services and to develop their own services. So they wanted to rent his field, and he was glad to have them do it. It gave him income that he didn't have to work at. So he rented on the field, and they had to set up and it was a real rolling fields too, and they had to set up airstrips there to bring in supplies and stuff by air and land on this uneven terrain. And that's what they needed to train their pilots to do, their ground crews to do, you know, how to build these things and stuff. So we had for about, I don't know how many years, a few years, that right next door to us. And that first night, we were in the flight path of those planes coming in. They had to deliver at night too, so they had to be trained for that. Flights were coming over us real low all night long. Every time a plane would come over, I'd wake up for one night. The next night, I slept through it all. Okay, but, so we had that. Well, those poor guys, they had to bring in all their water, and the water, this was summertime if I'm remembering right, or at least part of the time, and it was hot, and it was miserable out there, and they had only limited water supplies because that was acting like real warfare, okay? Well, they found out that just down the road from them on the adjacent property, there was a pretty, all of us knew about it, we hadn't even thought of it, there was an artesian well that we're going to be talking about right here. And that artesian well was always flowing. They also call it a flowing well. The reason it does, the pressure up here gets the water here and it flows. And it's called a flowing artesian well, or just an artesian spring sometimes. And that water, here's what's remarkable about it. It's such deep water that it's always right around the same temperature. Usually around 72 degrees. Which, if you can imagine, in the summertime in South Georgia, where the temperatures are in the 80s or 90s, if you had 72-degree water, that would feel wonderful to you. When they tanked it out there in containers, it would be close to 80-degree water, okay? But then in the wintertime, when it might be 40 degrees out there, that 72-degree water would feel nice and comfy. So what they did, the Army went down They rented from the person who had the artesian well that nobody was using anyway, and they rented that, and that's where they took the showers. In the wintertime, the showers were warm. They wouldn't have been back on the farm. And in the summertime, the showers were cool. They wouldn't have been back on the farm. So they really loved that. And then they could carry all the drinking water. It was all nice, pure, really good water. So I'm guessing we may be tapped into that same aquifer because we had to go so deep. And we're right up the hill from that. So we're across the road from the field that used to be the airstrip. Now over here, this could be us, the artesian well here. You drill a well here and you hit the water at this level. Whereas the aquifer is really here, but if you drill the water, the thing here, then the water will come up to that water table there. See, that's why this is artificial, because it's showing the water table above the water table yet. So this comes off here. But here, you're actually below the water table, and there you have a flowing well, just always spouting water. Now, there was the next county south of us, there was just this fantastic swimming area, and it was called Magnolia Springs because there was a artesian well coming up there. The trouble with that is, in 90 degrees weather, that 72-degree water felt awfully cold. You always are freezing in there, but in the wintertime, if they had had the pool open, that would have felt nice, okay, because it was 72 degrees. Had one other example like that. I don't remember what it is now. If it's important, I'll pick up it again. Okay, so that's what we mean by an aquifer. Any kind of aquifer is this underground stream, you might say. It's not solid. It's not all water. It has rocks and sand in here, but it's easily accessible water. Okay, and then the if it's artesian, then it's very deep, almost equal temperature, and then if you can tap into that with a well, very good water there or here. Okay, there it comes to the surface. Oh, I know, the other place was in Italy. We had a kid that lived with us one senior year of high school. We knew his parents well, and the girlfriend, when we went over to visit sometime after he had moved back to Italy, the girlfriend he was dating, then his family ran this fantastic restaurant. It's sort of a high elevation, but there were plenty of higher elevations around, and they had this flowing well right there. They had a restaurant. You ate outdoors. You know, it was just fantastic, great food, and they had this thing that you could just go over and fill up with water anytime you wanted to because it was a flowing well, and it was pure water. I mean, fantastic water. And most of the time in Europe, you don't get that much fresh water because they charge you for everything, and they give you small amounts. Here we get water is free most of the time. There, you could get just pitcher after pitcher full, drink all the water you wanted. You go out, got it yourself if you wanted to, you know, right there in the area right around there. Fantastic water, artesian water. Okay, nice cool temperature. That was summertime we were up there. So, fresh water as a resource. This is on page 613. Okay. Fresh water is required for life processes and modern industrial society. Life processes are important to me, okay? This is life processes for plants. They can't use salt water either, most of them. Life processes for animals, life processes for me. I hate to point it out, but Thomas Earl, you're pretty good about keeping hydrated, right? Yeah. And that's an important thing to do. And so it must be Rod too, because there he has water, and there Samaya has water. It's important, okay? We are mostly water. If you think about it, our bodies are mostly water. Required for life process. Fresh water. Incredibly important. Now this is hard to believe. The average U.S. usage of water is 570 liters per person per day. Now, you're probably not used to thinking in terms of liters, but would you look on your container there and see how many liters that is for somebody? Somebody? Maybe not. Thomas Earl, your container, don't you have one? Is that about a liter?
I got 2.
Oh, 2 of them. What is the bigger one a liter or more than
20 fluid ounces.
Is how much?
20 fluid ounces and then
And it doesn't have the
33.8 fluid ounces.
how much?
This one's 1 liter.
100.
This one's 1 liter.
1 liter, exactly. So that's a liter. That's a little more than a quart. Not much, but a little bit more than a quart. So if you divide this by 4, you get 140. Let's just round it, 150 gallons. 150 gallons per person a day? You don't drink that much, do you? Nowhere close. But it's not just drinking, by the way. This is our usage. 40% of that is used in agriculture to raise our food. Because guess what? That's done because of us, you know. So 40% is agriculture. 40% of that is to produce electricity. Whoa! Why? Well, most of the electricity is done by steam generation. So that's where most of that, they can't use salt water for steam generation. It has to be fresh water. In fact, it has to be purer fresh water than you're drinking out of your containers, okay? When I was in the Navy, we had to make our own water when we were out at sea, our own fresh water, and the best of the fresh water went to the boilers. That wasn't quite as good. That's what we got to drink. And sometimes it wasn't very good, but the best fresh water had to go to the boiler, producing electricity. And 10% industrial. Hey, most of this, of what we drink, flush, shower with and stuff, it doesn't even show up here. Okay. So most of the supply comes from surface water. That's where most of it is in the surface, not on the most of the supply comes from surface water. Just think about, I don't know where y'all live, but I live in Birmingham, and that gets its water from Lake Purdy. It's a reservoir of surface water. Are y'all more Bessemer area? No. Birmingham? No. Where? Where? Okay.
Hueytown, Pleasant Grove.
Okay, Hueytown, Pleasant Grove. Do y'all get your water from Birmingham Waterworks or from someone else? You don't. Huh? A lot of the communities get it from Birmingham Waterworks. I don't think Bessemer does. I think
mine is from Warrior River.
Warrior River, okay. So again, that's surface water, okay? Now, there's more sediments, there's more bacteria, there's more pollutants. So therefore, that surface water has to be treated, and treated pretty heavily. Filtered like crazy to get the sediments out, treated with chlorine or something like chlorine to get the bacteria out, and treated in other ways, maybe osmosis or something like that, to get the pollutants out, okay? It depends on precipitation. I remember several summers in the city of Birmingham when Lake Purdy got less than maybe 20 or 15% capacity, and they were getting really worried that we were not going to have enough water, and we had to go to rationing water and only watering laws twice a day, every other day, and sometimes even days, odd days, that kind of stuff. When you depend on surface water, it depends on precipitation. A dry summer, you get problems. I mentioned Lake Mead. Does anyone know what Lake Mead is? It's on the Colorado River. It's okay. First, does anyone know what dam Lake Mead is behind? The Hoover Dam. And at the time it was built, which was probably back in the 1940s maybe, 30s or 40s, it was the biggest dam in the world. Okay? Backed up an enormous lake called Mead. Okay? Enormous lake. Okay? The city of Los Angeles piped water a long, long way to use that water. Other cities in California did. That's why I said earlier, a lot of California, Southern California, which is pretty dry, got the water from the Colorado River watershed. I gotta think of the word. Okay. Well, they had had so many drought years in a row. Lake Mead was down significantly below its level, normal level, way below. Believe it or not, there had been a plane that crashed into Lake Mead back after World War II. Their pilots were doing training, or they were doing something, and they sort of lost where they were. They didn't. It was at night, and they crashed into Lake Mead. The plane went down, and it was so deep they didn't even bother trying to recover the plane. I don't know if the pilots got out or not. I don't know the whole story there. It got so shallow they could see the plane. And it had been so deep when the plane crashed, they didn't even try to rescue, to recover any of it. So that shows how much. So when you do get, most of your supply of fresh water comes from surface water, which is not the biggest source, okay? You have to do lots of treating, filtering, chemical, pollutant removal, all that kind of stuff, and you still depend on precipitation. Over 40% of our fresh water comes from groundwater, so that is probably close to 60% there, okay? The groundwater is relatively free of bacteria. That well on the farm, we don't treat that any way whatsoever. None of the wells on the farm did we ever treat. Now, my older brother has a mobile home on his part of the land, and he has to, it's not really treating, but he has to separate sand, because his well it pulls up sand, and he has to get that out of it. But other than that, he doesn't treat it with anything. We don't do it a thing. My sister does it, my brother does it, the farm pond well did none of it. So it's relatively free of bacteria and suspended particles, except my brother had sand in his. So there's no treatment required. However, it has to be pumped up from way below. So we use the money that would have been spent treating bacteria, pollutants, sediments, that kind of stuff. We spend it with electricity pumping the water up. In the old days, they used windmills to pump the water up, which was using wind power long before it got fashionable to use wind power. So fresh water is definitely a resource. We've got to have it. And look how much we use per day. Not that we drink that much or cook with it or anything else, but that is in the neighborhood of 150 gallons a person a day. A day! Nowhere would we use that in our homes. Most of it is in agriculture to produce our food, electricity to produce our electricity, or industrial to produce the materials we buy. Now, moving to seawater. Now, there was a table at the top of the page here on our average individual freshwater usage in the home. Toilet flushing, almost a quarter. Clothes washing, a little more than a fifth. Showering, about a sixth. Faucets, that's in washing dishes and drinking and everything else, that came up to about a little less than a sixth. And leaks and other wasted type areas, 19%, which may include watering plants and things like that as well. Okay. Bathing dogs, maybe, I don't know. All right. Before we get to seawater, there is oh, goodness gracious, we're almost out of time. Let me just say this. There is, remember we had a blurb on water quality on page 614 and 615, pages 614. There is a huge blurb there on water quality and wastewater treatment. Now, this is sort of a gross thought if you want to think it, but it's really reality. Every bit of water in your body was probably at one time or another in somebody else's body and has been expelled from that body. Because we don't manufacture more water, it's been reused and reused and reused and reused. There's probably at least one molecule of water in your body that was in George Washington's body. Or pick anybody in history, long ago in history, and you can probably say that's the case. Water is recycled, always. If it's not naturally, it's done by this wastewater treatment. Okay? Well worth a read. Very interesting. Okay? There's some things on groundwater being used for agricultural purposes, other things. We'll start next time with seawater. 24.2. Can't believe we've only gotten the first section done. That was a long section. And 21.2 is a very long section. And then 24.2, I'll be saying 21. 24.3, very short. So we've got it, more than a third of the chapter done. So I think we'll finish this. We may not finish it on Tuesday. Between Tuesday and Thursday, we will definitely finish the chapter. Knock on wood. So let's figure that if we don't have time to do the lab, we probably will. Okay, remind me again. We got Tuesday and Thursday of next week, and then only Tuesday of the following week. Is that right? Is that what we said? Okay.
Sounds right.
So we got, if we can get the field trip to Channel 13 arranged, that will be Thursday, and then the final exam will be, and the last chapter test, and maybe the last lab. If we don't get a chance to do the lab earlier, it'll be next week or Tuesday. And pizza will be Tuesday as well. All right, we'll end this.